Very good evening to all and welcome to our 5-day online faculty development program on applied mathematical skills for engineering and science using contemporary tools. We are organizing this FDP from Applied Science Department of MAKAUT in collaboration with Islamic University of Science and Technology, Jammu and Kashmir, sponsored by TechWave. Today in this panel, we have with us our Honorable Vice Chancellor Sir, Professor Shoikat Moitro, uh, um, Director of School of Natural and Applied Science, Professor Shukhendu Samazdar, Professor Radha Vallabh Bhatt, HOD of Applied Science, and our distinguished speakers, Professor Shubinoy Chakraborty from Jadavpur University, Professor Abhishek Odhikari from Presidency University, my colleagues Dr. Shankar Prasad Mondol and Ms. Anesha Sengupta from Applied Science Department, and I am Dr. Atrey Bishwas. In this program, as you feel from the title, some recent developments in the elite and applied areas of mathematics will be addressed, which includes topics like relativity to quantum mechanics, graph theory to fuzzy theory, cryptography, biomathematics to optimization problems, and different other topics related to applied mathematics. So, I believe this FDP will help our participants to identify the areas of current and ongoing research in mathematics, develop a conceptual approach in teaching in mathematics, and finally to understand the applications of mathematics in real world problems pertaining to engineering and industries. Now, we shall have a short session followed by our lecture session. So without taking any more time, let us start our inaugural session. I shall request our Honorable Vice Chancellor, Sir, kindly to inaugurate the program and to share his valuable thoughts about this program. Sir, please.
Thank you, Dr. Atrey Bishwas. I am overwhelmed to see this, this power of activities from Applied and Natural and Applied Science Department in organizing so many faculty development programs, trainings, workshops, webinars. It's great that we have taken a very good initiative in line with.
Sorry, sir, to interrupt. Actually, we can't hear you.
It was okay, at least with me, it was okay.
Yes, sir, you are audible, sir. Please continue.
Yes, sir, audible.
Okay.
Okay, it's okay.
Okay. So what I was saying, this is the problem with these digital systems. One of the greatest advantages, what we can see in morning we had another programs, in afternoon we are going to have another programs. After 1 hour there will be another programs. So numbers of programs are being organized from this university, and I have to attend today. I already attended 3 programs, and I have to attend 3-4 programs more. So from this university and from other universities institute as well. These are the biggest advantage of this time of digital technology. But the problem is this: sometimes due to this communication bandwidth problems, sometimes there is this voice is not clear, or there may be disconnections with the systems, and this has become a part of our culture. And every time we have to repeat that whether I am audible, whether I am visible, whether you can see my presentation or not. So these are part of these systems. So that's okay, but this is a new culture, and I'm proud to announce that my university, or rather our university, we have embraced this culture from the very beginning. When this lockdown process started, as a part of this government decision in the month of March, from that time only, along with all our faculty members, all our directors, we initiated this teaching learning processes, this academic program through digital platforms for the benefit of a large number of learning communities, not only associated with our university systems. I can see many persons they are joining from other institute as well. And of the late, we have integrated this effort with our one of our partner university, Islamic University of Science and Technology. They have also taken up this activity. I was personally present in one or two of their activities of the late, and this is a very good sign. Because there are two thought process available. One group of people are saying that we will be going to have this again all the things, normal things again, but some other group of people are telling that the situation, the world will not be the same again even after this pandemic scenario. Whatever it is, this is the time to use these digital platforms, and we have to this accustom ourselves with different tools and techniques and process methodologies, the culture associated with these digital cultures. And 5 day every program is a good. What I can I would like to mention one thing. A couple of years before, we wrote a letter to UGC requesting that this faculty development program should be allowed to this organized through this digital mode, because of the fact that saves lots of time. Because the conventional faculty development programs, which was there earlier, the faculty, they have to go from their university taking leave to some other places to attend the programs, and that seriously affected these academics, ongoing academics of that particular university, because of the constraint in the numbers of the faculties associated. For example, in any department, there may be a limited number of faculties, and this is a responsibility for the university to allow all of them to upgrade their knowledge and skills by joining to faculty development programs, and this is a part of their promotional, this aspect also. But that created lots of problem for the students, because when the faculties are not there, these ongoing academics that suffered a lot. So these were our experiences, and we wrote this letter to UGC, and perhaps we are the first university of this country to initiate this faculty development program through digital mode. This is one of the this our endeavor that I'd like to say. We had taken other initiatives also in digital for adopting and for utilizing these digital platforms to the best possible extent. But this is one of the very important things which we initiated 2 years after that. UGC endorsed it, and now faculty development programs through digital platforms, this is very, very much valid, and that will give this equivalent, this as much credit what was there earlier for normal faculty or traditional faculty development programs to all the participants who are here. So this is one of the good thing. And another advantage is this in other times, this getting the resource persons from different parts of the country or maybe other parts of the world, it was very difficult. Within a short possible time, we could not organize it. But right now, this is very much possible, very much feasible, and very much this formidable. So what we are seeing that because of these advantages, we could invite, we could assemble a large numbers of experts, doyens of their fields from different universities, different institutes, and this has created this lots of knowledge repository. And so far hundreds and hundreds these webinars, training programs, and workshops we have organized. These faculty development programs we will be organizing in a continuous manner in near future too. And I believe that by way of doing this, at least this a certain level of knowledge improvement of all the participants who are present over here, that will happen. Now, let us come to today's topic. This applied mathematics, it's very important area, and considering the importance of these subjects, we have decided to introduce academic programs in applied mathematics. And what we are seeing that in applied mathematics, there are lots of career options available, and because it is a pivotal subject, and we can see that so far our the survey the report is concerned, we have seen that that graduates with applied mathematics or postgraduate applied mathematics, they have potential careers in a diverse fields, starting from aerospace engineering, starting from accountancy, architecture, artificial engineering, intelligence designer, specialist in bioinformatics, then climatologist, city planner, a computer security analyst, database developer, then a hardware developer, logistics specialist, then national security analyst, operation director, product developer, risk analyst, reliability engineer, satellite communication specialist, environmental scientist, financial analyst, what's not, statistician, software engineer, developer, system designers, forensic specialist, entrepreneurs, engineering consultancy, in many areas. Applied mathematics, this role of applied mathematics are becoming more and more, this important, they're getting more and more importance. And that's why it is our sincerest, this intention to introduce a course in applied mathematics. Already we have taken initiatives in that directions, and through applied mathematics we want to produce a large number of experts in this field to take care of these diversified fields. We believe that it will have a very successful career, career propositions after this taking up these types of programs. And I tell it at every occasion that this is my appeal and advice to all the participants who are here. So whatever you are learning from this faculty development program, that has significance, but at the same time, try to gain more knowledge from online platforms, from digital platforms, from open courseware. There are plenty of resources, plenty of courses, plenty of these materials available in digital domain. So along with this knowledge, whatever you will be gaining over here, if you supplement with the this further knowledge from digital platforms, from online platforms, through MOOCs, through open courses, all these things, it will give you a very formidable this knowledge for applications in your own area, or to take up these further researches. So and that will give you this a good advantage in terms of your this knowledge and skill. So with this, I wish this faculty development program a grand success. I congratulate Dr. Samazdar, Dr. Bhor, Dr. Atre Vishwas, Dr. Shankar Mondor, and all others who have organized it. And my best wishes to all the participants. I wish all of them a very enjoyable learning, effective learning, and my sincerest thanks to the resource persons who have come over here, who have to share their knowledges, to share their experiences and ideas with our learning communities. Thank you all.
Thank you very much, sir, for your thought-provoking and insightful address, and thank for your encouraging words in conducting such type of programs, particularly through virtual platforms. You rightly point out that is gaining importance more and more and becoming pivotal and has potential career prospects. So in this perspective, we shall surely try to organize such type of programs more and more. Thank you very much, sir. Now I shall request Professor Shukhendu Samazdar, Director of School of Natural and Applied Science, to say few words about our program. Sir, please.
Thank you and namaskar, Honorable Vice Chancellor of Maulana Abul Kalam Azad University of Technology, distinguished guest speakers, respected fellow panelists and participants. It is a privilege to welcome you all to today's session in applied mathematics and its different tools and its applications in line with the modern development. Now, let me introduce the school I belong to and give you an overview of our activities. Just This is the School of Natural, Applied and Social Sciences. We used to be Natural and Applied Sciences, but from this term, we are introducing courses in social sciences as well. So welcome on behalf of MAKAUT, on behalf of the School of Natural, Applied and Social Sciences, as well as on behalf of the organizers and my own personal behalf. This is how the school is structured. Essentially, there are several departments and different divisions, academic divisions, domains rather, which offers different subjects and the courses. This term, we are offering 13 in-house programs in the academic year. Those are spread all over the place. There, as you can see, there are quite a few in mathematics. There are the BSc in mathematics with computer applications, MSc in applied statistics and analytics. And so these are different courses that we have. Focus. The academic focus in general for the school is on computational applied science. Nowadays, mathematics and computation are married together a lot more. Any non-trivial mathematics, actually, most of the non-trivial mathematics rather, requires computational and numerical techniques. We are aligning ourselves in that line. There are the other area of focus is nanoscale investigation in general in the school. But that does not necessarily mean that we neglect other areas, but these are our focus areas. Organizationally, we are focusing on growth together with quality. As you see here, that in 2018 there was only a single program, in-house program, while in 2020 we have 13. 2018, the school had 6 faculty members, while today we have 14, and we are recruiting more. In fact, as we speak, there is an advertisement for mathematics faculty active on our website. Now, just because we are growing doesn't mean we are doing it at the cost of quality. In a university, the quality of faculty matters a lot. And we are proud to say we have one Alexander von Humboldt Fellow amongst us, one Nehru Cambridge Fellow amongst us. There are people with doctorates from the University of Michigan, Ann Arbor, Indian Institute of Science, Bangalore, and institutes of here the school is the recipient of multiple DST grants, and the faculty members routinely publish in high impact factor journals, and we have members who are senior office bearers in professional societies such as the Institution of Engineers and the like. Our scoreboard, as you can see, as Honorable Vice Chancellor has pointed out, we have been very active right from the beginning. There was no slowing down. Actually, we geared up a notch or two during this lockdown and engaged ourselves, engaged our students, encouraged ourselves as well as the students, and educated the students as well as ourselves on this online medium. There are several activities that has taken place, and the student and faculty engagements, we are very proud and happy to say that there has been an increasing student and faculty engagement along through this medium as well. Our motto, if I may say, is one for all and all for one. It's basically the foundation principle of teamwork. And our modus operandi is dismantling the boundaries between the departments. So we try to work together, and we work together, and we are holding FDPs like this, which are actually interconnect, which reflects the interconnected nature of science. Science of materials, I have put it because most of the applications of science, a large amount of applications of science are in the domain of materials. Some are in the domains of energy, as of course. Here, as you see, that math is connected to pretty much all the other so-called specializations. And centrally here is the computing power and the user friendliness of computer tools. That has significantly risen over the last several decades and is helping mathematics and quantitative techniques in pursuit of science, education, and research. Now, in matters of mathematics, I am basically a blank head. I was not very much interested or good in mathematics while I was young. However, my interest in mathematics was stimulated or sparked by art, especially the art of a very famous Dutch graphic artist, M.C. Escher. The famous paintings or graphics such as hands on the Mobius strip, or the hands drawing hands, or the reflection, all these are founded in sound mathematical principles of symmetry and reflection and topology and etc. Of course, I would be amiss if I do not mention the golden ratio, the classical Vitruvian man of Leonardo da Vinci. So this beauty, actually, a sense of beauty, a sense of implicit beauty, a beauty that cannot be seen but has to be realized within, has been the inspiration for me to learn whatever little bit of mathematics I know. And I would hope that during these 5 days, discussions will focus not only on the techniques and tools of mathematics, but at times would hint at its underlying and humbling beauty as well. Thank you.
Thank you very much, sir, for your insightful and effective overview about our school and department, about the programs we are conducting, and about to start in future in line of computational mathematics in such a concise manner. And thank you. Thank you for all the informations you have conveyed to our participants about our school and department. Thanks again, sir. Now I shall request our HOD sir, Professor Radhavallabh Bhatt, kindly to share his views about our program.
Honorable Vice Chancellor, I am audible.
Sir, can you be a bit louder, sir?
Oh, acha.
Now it
Yes,
is good.
it is
Now
coming.
it is
coming. Now it is
coming.
coming.
Now it is good.
Acha, okay.
Yes, yes,
Okay, okay.
it's good.
Okay, thank you. Honorable Vice Chancellors, my director, Samazdar, panelists, all speakers, and also participants. I am very happy that our department is organizing such a repeated, means not repeated, more than one program within same day. They are starting same day 2 programs. So it is possible only due to the fact that Vice Chancellor already mentioned that because of the digital mode, it is possible. If in the offline mode, it was not at all possible to organize such a short time to organize two consecutive programs from the same department. It is obviously an advantage for us to organize such program in digital mode. So we have to welcome this type of program in future also, so that with less time wasting, with less time, less mind, and effort is also to some extent less, we can say, because of the fact in the case of offline mode, to organize one FDP, we have to spend at least 2 months, because for collecting all the speakers and assembling it to the campus or some location, it is very difficult in that sense. And at the same time, I am observing that now we are 105 participants. So 105 participants is not possible to organize in offline. So in that case, limited size of our, say, classroom or facilities, lab, in the case of lab-oriented lab facilities, though it is difficult to organize hands-on experience over here, but maximum part of the program can be transmitted to the participants, and if they try themselves or they feel any difficulty, then they can contact with the experts and they can gradually develop themselves. So we are also learning by getting inspiration from our vice chancellor that we have to learn the different tools available in the digital mode. And gradually I am also learning, because my study period was in bulk and transistor, discrete components. IC was not there. So gradually I have learned IC, gradually I have learned microprocessor, and last few years in my previous institute, I teaches microprocessor also. So this is gradually developing, and now the situation, particularly pandemic, forced us to learn how to conduct different programs in digital mode, how to conduct virtual lab, how to conduct different facilities available, and how to utilize the different tools available. So gradually I am also learning, and it is a good that still my mind is trying to understand the situation and to trying to learn. So in this situation, obviously this platform is obviously like Vice Chancellor, I also feel it is good, and we have to utilize it. We have to utilize as our level base, and whatever, how much we can, best way we can utilize that, we have to think. Obviously some difficulty is there, but that we have to accommodate, that we have to know the difficulties, and within their limitations we have to continue. But still we have not stagnant. We should not be stagnant ourselves. We should roll ourselves. So this is the way by which these programs has been organizing within very short period. So we are very happy and thankful to the whole organizers, particularly Dr. Atri Vishwas and Shankar Mondal. Their maximum effort they have given, particularly for this FDP. Our director also given continuous input, because he guided us continuously. Then what is to be done, what is the checklist, what are the things to be done to make it fruitful, or to be, say, instead of webinar means it is an international program. Anybody from anywhere, can join. So that the program should be of that standard, so that our university should maintain that proper standard of international level. So that we have to do it properly, and that care has been taken by our organizer, Dr. Atri Vishwas and Shankar Mondal, and our Vice Chancellor and Director Riley has already explained about the total situation, what is the importance of applied mathematics and contemporary, with the help of and techniques of contemporary tools. So, and our director also explained about our department and school, how it is growing. So it is a good sign. Obviously, he has shown quantitatively how it is gradually growing. So I am also happy to be part of it. But here I must want to express my thanks, particularly participants and honorable speakers, because both they are the main criteria, main energy to organize such program. Our success depends on the program, how we are organizing and how much participants are absorbing from the speaker, how much amount of knowledge transferred to the participants, and from that, from the idea, from their feedback, I will be able to understand it, and I think all of the participants will enjoy in the next 5 days, and I hope this program will be a grand success and it will achieve its goal. With this, I want to thank again to all organizing people and all panelists also. Thank you all, sir.
Thank you, sir.
Thank you very much, sir, for your encouraging words in conducting such type of programs through digital platforms. At least in this situation, which is and digital platform, as you said, is most essential for today's learning. And we also want to thank you for all your support in conducting today's FDP. So with this, we end the inaugural session here. I thank all the dignitaries for gracing this session with their benign presence. We shall now start today's lecturing session. I welcome cordially our first keynote speaker, Professor Shubinoy Chakraborty, in our program. Professor Shubinoy Chakraborty, sir, is a very well-known and eminent professor from Mathematics Department of Jadavpur University with about 38 years of teaching and research experience. He has guided more than 30 PhD students and have about 281 publications in various national and international reputed journals. His areas of research are mathematical physics, general relativity, cosmology, study of topological defects, and quantum gravity. We feel fortunate enough to have him among us today. The title of his lecture is Relativity and Layman's Perspective. I'll request Sir kindly to start his speech. Sir, please.
So, thank you all. First of all, I think that this much of introduction is not needed because I don't think that these are very useful for introducing a speaker. Okay, in any case, my title is that Relativity Theory, a Layman's Perspective, because frankly speaking, I know very little of mathematics. So that's why why I have that courage to speak something related to mathematics, because so far whatever I have learned, I learned mostly from my students, because by conversation with the students, by answering several questions of the students, so I learned a lot. So this subject, this relativity theory is a similar example of that, which I learned mainly by interaction with the students. Now here, why I call is a layman's perspective, because I have no formal any learning ability about this relativity theory in my college or universities. So I learned mainly by interacting with the students. And that's why I call it a layman's perspective. And another thing is that I will not describe this lecture just in the conventional way, because in the almost in all the books, the relativity theory is developed almost in the way Einstein has formulated it. So I will not talk it in that way. I try to develop it more in a mathematical or in particular in a geometric way. But before starting that, I will say a few words about the history of the relativity, and then I will go over with some curious thing that I have in mind, and I try to find whether they have any connection with this relativity theory. Now, all of us know that relativity theory was invented by Einstein. So that is true. But the idea of relativity was started long back, since the time of Galileo. Because in very ancient time, that idea of relativity was there. What is that idea? The idea was that nature is very neutral. It has no partiality to any observer, to any space in the universe. So whatever an observer is seeing, any natural events, that should be the same identical for all observers at what place, whatever place it will, that observer was. But practically we are not observing that like things. So people had that idea that it should be, but that we are not practically, we are observing. So that's why that was more or less going in that way. Formally, it comes into the formulation by Einstein. So we just say how Einstein derived it, what Einstein had in mind to derive this relativity theory. I mainly speak on the special theory of relativity, and if time permits, I will say a few words about the general theory of relativity. Okay, so before starting that, I start with that. Suppose we know all that, we have all in mind that 2 plus 3 equal to 5. 2 plus 3 equal to 5. Okay, 2 plus 3 equal to 5. Now, if one day it is not 2 plus 3 equal to 5, then what happens? So that's my first question. Suppose 2 plus 3 equal to 4, then what will happen? So that is my first question, because all of us know that 2 plus 3 equal to 5. So if it is not 5, then what will happen? That's my first question. So I start with that question. So I do it in a more general way. Suppose A plus B. So as I am not conventionally 2 plus 3 equal to 5, so that's why I've given the plus sign in a different way, just with a circle around that. So if I suppose that A plus B is not A plus B in the usual way, but suppose it is in that form, A plus B by 1 plus A. If I calculate that sum like this, so I can simplify it in that form. So I can write it in that form. It is very simple algebra that you can follow. So it is like that. So I extend that. I take the sum of 3, A plus B plus C. And in the similar way, I can write it in that way. 1 minus this. Now what we can observe from here? Now from here, A plus B equal to what I have seen. That from here, we see that if A is less than 1 and B is less than 1, then from here, I immediately see that A plus B is less than 1. So that I immediately see. Similarly here, if both all A, B and C, all three are less than 1, then A plus B plus C is also less than 1. So this I can conclude from here. So now I try to extend it further. So if I extend it further, I now write it in a general way. So instead of A plus B by 1 plus AB, I write it A plus B by 1 plus AB by lambda square. Lambda is a real number, is a positive real number. So I write it in that way. So if I do the same algebra as here, I get it in that way. Now what here I get, if A is less than lambda, B is less than lambda, then from here I see that my addition A plus B is also less than lambda. So that I can conclude from here. Not only this, if I add A plus lambda from here, if I write instead of B, I write lambda, if you calculate it, you get it lambda. And similarly, if I write A equal to lambda and B equal to lambda, again, I calculate lambda plus lambda, I can get only lambda. So that's a peculiar addition we are getting. Just we deviate from the usual addition that we know slightly. And after this, we are getting a peculiar result. Now, I can interpret this result in a different way. I can say it in that in ancient histories or in ancient stories, there are some ancient stories where we see that there is a king, and that king always gives his wealth to all his peoples. But he continued to give it, but never his wealth has becomes empty. So these are some stories like there. So some mythological stories are there. So that stories, I can interpret it here in terms of mathematics, because there I am giving the wealth to the peoples. So I am just adding the wealth giving to the peoples. Now, if I addition there is not the usual addition we have here, 2 plus 3 equal to 5, but the addition rule is like that, a plus b equal to a plus b by 1 plus ab. There you can see that, or I can write it as a plus b equal to a plus b by 1 plus ab by lambda square. That means I am giving someone wealth of amount 2 and 5, 3 to some other. Then I add 2 and 3, the sum of the wealth. If I add these two, if I add in that fashion, that is less than lambda. So I continue it for, if I continue it for more and more, I give it to all people, but still I have something in my box, because whatever I am adding, a plus b plus c, whatever I am adding, that sum is always less than lambda. So lambda is the total amount I have with me, and I am now distributing to the peoples. If I am distributing, whatever number of the peoples we have, at the end I must have some amount within my that. So whatever number of peoples I am giving them, still I have some. So that is possible using this addition. So those mythological stories I can explain simply with this type of addition, not in the usual addition. Okay, so that's a different story that I am telling simply like this. But here, this addition rule has an immense application. And that application I am telling, that is one way we can interpret relativity. So I am just starting with a simply algebraic sum. And from this, with a peculiar sum, I am getting a peculiar thing. I am getting a real number lambda. So if I choose any number less than lambda, I cannot cross that lambda. Whatever way I am doing, so I cannot cross that lambda. So I add something with lambda, I always get lambda. If I add lambda with itself, I always get lambda. So always, if I add this lambda with anything, or if I add in two numbers less than lambda, so I can never exceed lambda. So that's the idea here. So that idea can also lead to the special theory of relativity. Because what this relativity theory tells us, this relativity theory tells us, that is the formulation of Einstein, because that universal, what I say, that uniformity of the universe, that is the basic theory of relativity that is known since the time of Galileo. But with that idea, Einstein has introduced another hypothesis to that, and that gives us the special theory of relativity. What hypothesis he has given? He has given that velocity of light doesn't care about the relative motion between the source and observer. It is always universal. That means whatever the motion of an observer, every observer sees the velocity of light uniform, identical. So that's the idea. Why Einstein put this hypothesis? What's the background behind that? Because background is that there are some experiments going on at the end of 19th century, where it is found that the velocity of light does not depend on any relative motion between the source and the observer. So that's idea puts, and that is contradicted by the Newtonian theory, because according to Newtonian theory, velocity of light should depend on the frame of reference. That means depend on the observer. If the two observer has a relative motion, then the two observer must have different velocity of light, according to the Newtonian theory. But that experimental result totally contradicts the Newtonian theory. So though at that time Newtonian theory is the supreme theory, so physicists or the experimentalists, they have that idea at that time. Probably they are making some wrong experimental setup, so that's why they are getting such a conclusion which is in contradiction with the Newtonian theory. But Einstein at that time only thinks in that way, that is it true that velocity of light is identical? So starting from there, he formulated the relativity theory. So that he put as the postulate. And just putting that postulate with the universal identity of the nature, he formulated the special theory of relativity. And conventionally in the books, they have developed the relativity theory in that way. So here, we shall not do in that way. Now here, I just give algebraically a flavor that if I just deviate from the conventional idea of addition, I am getting a peculiar thing. Now we shall show that can we apply this into some other physical theory which has an immense application of this? So that we shall do. Now before that, now we shall show that relativity theory can be derived purely from the mathematical point of view. Or more specifically, we can say that relativity theory can be derived purely from the geometric idea, simply from the axiom of Euclid. So here I shall show how purely from the axiom of the Euclid we can develop the relativity theory. So I very briefly go into that, and here I just show that sum of these two is this. Now, before going to the geometrical ideas, how relativity theory can be developed using that, here I shall say one thing, that whenever we talk about the relativity theory, you can see everywhere Einstein always speaks about space-time. Space-time, he always speaks about. So, but we have only the idea of space. We have no idea about the space-time, because in the Newtonian theory, or according to the Newtonian theory, time is universal. Whatever time I have is same or identical to a person who is in a moving train, because time is absolute in the Newtonian theory. So time does not change from observer to observer. But Einstein first speculated that idea leads to the case that Newtonian theory, if time is absolute, then we cannot have, it is not possible that velocity of light should be constant or uniform or identical for all observers. Why? Because we know that velocity, that we can define as dx dt. X is a space coordinate and t is time. So rate of change of velocity, velocity means rate of change of space travel divided by time. So it is simply dx dt. Now you know that in Newtonian theory, Euclidean geometry is the geometry. So x is unbounded because space is unbounded. We can move anywhere from minus infinity to plus infinity. So x is unbounded. But in Newtonian theory, time is absolute, time is fixed. So you know that x is unbounded and time is fixed. So that's why velocity is unbounded. It should be unbounded because numerator is unbounded but denominator is bounded quantity. So always velocity should be unbounded. So if velocity is unbounded, the velocity of light cannot be universal. It varies from one observer to the other. But if we assume that the velocity of light is universally same, it's a finite quantity. If we assume that, so that is possible only if time is not absolute. Time also varies from observer to observer. So what it means? It means that as space can vary from finite to infinite quantity, time also varies up to extent to up to infinity. So if I have two infinite quantities, then their ratio is a finite quantity. That is possible. So that's why light speed is finite. So Einstein then speculated that time is not universal, it is absolute, it is relative. It varies from observer to observer. So whatever time I have is not identical to an observer who is in a moving train. So time gets slow to a moving observer. So that's the idea of Einstein. So as space is changing, time also should be changing. So that's why Einstein called it as a space-time. Space-time means similar to space, time also move. So space and time in a combined 4-dimensional space-time. So that's the space-time where Einstein formulated his special theory of relativity. So we shall always talk about the space-time, 4-dimensional space-time. So that is simply Einstein in mind, and he just developed it in that way. But the idea behind is that purely from mathematical point of view, and this, so that I have mentioned here that time is a relative notion. So now I am coming to the geometric idea. So we know the Euclid axiom. What Euclid axiom say? The distance between 2 points is invariant. Invariant means that it doesn't change from one coordinate system to the other. If I move from one coordinate system to the other, but the distance between the 2 points remains same. It is one of the Euclid's postulate. So I start with the 3-dimensional space. So I have 3 coordinates, x, y, z. So if I consider 2 neighboring points, one point has the coordinate x, y, z, another one has the coordinate x plus dx, y plus dy, z plus d. So simply the distance between them is dl square, which is dx square plus dy square plus dz square. And it is an invariant quantity according to Euclid's postulate. So as we are trying to introduce the relativity theory, so we go over to 4 dimensions. So if I go over to the 4-dimensional space-time, so I have now 3 space coordinate x, y, z and 1 time coordinate t. So now I have the 4-dimensional invariant quantity dx square plus dy square plus dz square plus dt square. So that should be invariant according to the Euclid, but it should not be correct. Why it should not be correct? Because you know that whenever we add few quantities, then all these quantities must have the same dimension. Here you know, see that on the right hand side, the first 3 terms, this dx square, dy square, dz square, it has the dimension of length square. But the 4th term is the dimension of time square. So these are 2 distinct dimensional quantities. So we cannot add them. So it is not a well-defined quantity. So there is no question of invariance of this. So we have to first properly formulate it. So in order to make a proper formulation, we consider it in that way. So I consider it that lambda square dt square. So here lambda has a dimension of velocity. It's a constant quantity, but it has a dimension of velocity. If it has a dimension of velocity, then lambda into t, velocity into time, has the dimension of length. So then this quantity has the same dimension as the first 3 terms. So now this is a well-defined sum square and square of sum of the squares. And this I can claim according to the Euclid's postulate is an invariant quantity. Okay, so this is an invariant quantity. So it invariant means that if I consider 2 systems of coordinates and I just put it here and I take that dl4c square should be invariant. So if I equate what I get simply the Euclidean transformation that we know from before, since the time of Galileo. So we don't get anything new. So now here we have to consider one fundamental quantity or one fundamental property of time. We know that from space, it is reversible, because for space I can move forward or I can move backward. But for time, I can move only in the forward direction. I cannot move in the backward direction, because starting from here, I cannot go to the moment from where I started my lecture. Okay, so that is not possible. So for time is irreversible, but space is reversible. So that property I have to take into account here. So how we can take into account that property, that although we are considering space-time, but still time has a special status compared to the space coordinate. So that is the major difference between the space and the time coordinate. So how we can accommodate that? Now, in order to accommodate or in order to distinguish the time coordinate from the space coordinate, I just put a very simple change in this quadratic form. I put a minus sign in front of the dt square. So that I write simply as this, So dA square, which I write dx square plus dy square plus dj square minus lambda square dt square. And according to the Euclid's postulate, I call that this is an invariant quantity. And now here dA square, that I called as space-time interval. So this space-time interval I called as an invariant in the fourth-dimensional space-time. Okay, so now this is an invariant quantity. Now why this minus sign is important? So that has a mathematical implication. Why? Because you see that dA square is a quadratic form. So it's a quadratic form, but it is not positive definite. Previously it was positive definite, but it is not positive definite. It has 3 plus sign and 1 minus sign. So it has signature plus 2. Signature is number of positive term minus number of negative term. So it has signature plus 2. And we know that in coordinate transformation, a quadratic form always retain its signature. So if I make a coordinate transformation here in dA square, its signature should be plus 2. Now, out of 4 terms, if the signature is plus 2, then I have only one possibility. I must have 3 positive terms and 1 negative term. So after transformation, I get a similar like of terms with 3 plus sign and 1 minus sign. Then I can identify the time coordinate. The coordinate appears with the minus sign must be the time coordinate. So I can easily identify which one is the time coordinate. So for that, I restrict myself only that irreversible character of the time. So I can easily do that. So that's why I put a minus sign. It is purely from the property of the quadratic form. So I put a minus sign there so that this is an invariant quantity. Okay, so now I put a coordinate transformation. So for simply, what type of coordinate transformation I choose? So I take 2 frame of references. One frame I identify as the S frame, another frame I identify as the S frame, S dash frame. In S frame, the space and time are identified as X, Y, Z, T. In S dash, it is identified as X dash, Y dash, Z dash, and Z dash. So these are the 2 frame of references. So then I have, so if dA square, that means space-time interval is invariant, then dS dash square, which I can write in that way, and that must be equal to dS square. So these 2 must be identical. If these 2 are identical, then what I get? Now here you see that by construction of these 2 frame of references, how we constructed them. So I have Z and Y and Z axis, they are parallel to each other. And X and X dash axis, they are incoincident. And the S dash frame, whose origin is O dash, which was initially coincident with O. Initially it was incoincident with O, but it moves with constant velocity V along the common X axis. So at any time T, it is at O dash. So that's my idea. So as the frame S dash frame is moving with constant velocity V along the common X dash axis, Y and Z coordinate has no changes. So I can put easily that Y dash equal to Y and Z dash equal to Z. But I don't know about X dash and T dash, how they are related with X and T. So for that, I choose linear equations. That linear transformation equation, like that, X dash equal to this and T dash equal to this. Why I choose the linear equations? Simply mathematically, I can say that for simplicity of calculation, I choose only the transformations which are linear in nature. So that's why I choose, because first I start with the simple one, how it transforms, how it behaves, that I shall want to observe. So that's why I choose the linear transformation. So here A, B, alpha and beta, those are independent of the coordinates, but it may depend on the relative velocity V. So A, B, alpha, beta, they may be function of V at most, but they may be constant. But they cannot depend on the space or time coordinate, because then they no longer be linear. Okay, so later we shall show that if they are not linear, we will not get the special theory of relativity, because special theory of relativity only relates to the inertial frame of references. If inertial frame of references we are talk about, then that always deal with such type of linear coordinate transformation. If we have the nonlinear coordinate transformation, they are no longer the inertial coordinate transformation, they are nonlinear coordinate transformation. So in special theory of relativity, we only consider the linear inertial frame of references. So that's why we are only linear coordinate. So now here, what's the basic idea? So here I have dx dash equal to this and t dash equal to this. So I calculate dx dash, which is a dx plus b dt, and dt dash, which is alpha dx plus beta dt. So I substitute here. So instead of dx dash, I put a dx plus b dt, and instead of dt dash, I put alpha dx plus beta dt. And I put equal to ds square. ds square means dx square plus dy square plus dz square minus lambda square dt square. Now you note that dy dash equal to y and z dash equal to z. So dy dash square and dz dash square gets cancelled with dy square and dz square. So now I have three terms. What type of terms they are? One term is dx dash square, one term is dx square, one term is dt square, another term is dx into dt, that product term. So, and this is equal to 0. Now here you see that dx and dt, they are totally arbitrary because we are dealing with the coordinate transformation, any arbitrary coordinate transformation. So all the coefficient of these three terms should be 0. So that we can do. So here I have just shown that from ds dash square and ds square, they are equal, and from there I get three equations. So I am not shown here detailed calculation. If anyone interested, they can easily show it. That if I equate these two, so I have just I mentioned that I have three terms. One term is coefficient of dx square, one equation related to coefficient of dt square, and another equation related to coefficient of dx into dt. So now I have three equations. Three equations involve what? Three equations involve these four unknown coefficients, a, b, alpha, beta. So I have three equations with four unknowns. So I cannot solve them numerically. So in order to solve them numerically, I need one more equation. So that equation I can derive from the construction of these two frame of references. How we can construct those? Now you observe that if I consider the plane x dash equal to 0. So I consider the plane x dash equal to 0, which is y dash z dash plane. So the plane x dash equal to 0, so it is in the s dash plane. If I observed it from the s plane, so that will be x equal to vt, because the distance it traverses v into t in time t. So this is x into x equal to vt. So when x dash equal to 0, x equal to vt. So I substitute here. X dash equal to x plus vt. So x dash equal to 0, I put it 0. X equal to a vt. So I take t common. So I get av plus b into t. And that is true for all t. So I get simply b equal to minus ab. So it is very simple. You can get another equation related to this coefficient, that b equal to minus ab. So then I can solve these four equations. If I solve, I can find out the transformation equation. The transformation equation that we obtain, that will be given by this. So gamma is the relativistic coefficient that is known as, it is 1 minus v squared by lambda square. So these are y dash equal to y and z dash equal to z by construction, and this is x dash and this is t dash. Now here, I must mention that this simple type of coordinate transformation we are getting as we consider the frame s dash moving relative to s frame along the common x-axis, so that y dash and z dash are parallel to y and z, and there is no change in the y and z coordinate. But it is possible that I move any arbitrary direction, not in any prescribed axis, any arbitrary direction, then also we can derive such type of coordinate transformation, but they are lengthy. We are not going into those details or lengthy calculations. We just give you the flavor, how relativity theory can be constructed. So that's why we are dealing with the simple cases. So that's the transformation. Now this transformation was already also derived by Einstein. And how he has derived that? He has derived that with those two postulates. One postulate that is known since the time of Galileo, that nature is universal, every frame of reference should have the identical observations. So that is the first postulate, and the second postulate, they have considered that velocity of light is universal. It doesn't care about the relative motion of the source and observer. So using those two postulates, Einstein formulated this transformation. Why the name Lorentz transformation for this? Because before Lorentz already derived such type of transformation. But unfortunately, he couldn't interpret that. What result he has obtained? He got mathematically this type of transformation, but he couldn't interpret what's the interpretation or what is the implication of this transformation. So when Einstein started that, he found that in the literature that is already there. Lorentz before him has already derived this. So he simply collected that transformation, and in honor of Lorentz, he termed them as the Lorentz transformation. So this is the Lorentz transformation. Now here, interesting thing is that without assuming those postulates, without assuming the major one that the velocity of light is invariant, we can derive the Lorentz transformation. So what we have assumed? We have assumed simply the well-known Euclid axiom and the well-known the quantity, the property of time, that it is irreversible. Just using these two, we have derived the Lorentz transformation. We have not assumed anything on the physical ideas. And only thing here is that I have the transformation. Here only one thing that is related to physics, that is lambda, that has the dimension of velocity. Now, here interesting is that we have derived the Lorentz transformation where we have not talked about anything about the velocity of light, but we have derived that. And you can see that in the book of any special theory of relativity, if you put lambda equal to c, you get identical Lorentz transformation as is there in the relativity. So we have chosen lambda, any arbitrary positive real number, and there they are obtaining or specifically considering lambda as c, the velocity of light. But in course of my lecture, I will not talk about c. I will always talk about lambda, any arbitrary absolute speed. I don't know whether that speed is related to light or any other quantity. So I just put it as the lambda. Okay. So that's the Lorentz transformation. So that I immediately obtain. And if I want go back to the Newtonian theory, because from relativity theory you can go back to the Newtonian theory, and that is possible if I put lambda goes to infinity. And I have the Galilean transformation. That is the go to the Newtonian theory. What it implies that lambda goes to infinity, what it implies. Now lambda goes to infinity, it means that lambda is enormously large compared to the relative velocity v that we are considering. So relative velocity v is very, very small compared to lambda. That's the idea, and that's why it is making that lambda goes to infinity. So if the velocity or if the relative velocity between two observer or two frame of references is very, very small compared to this absolute speed lambda or invariant speed lambda, then we can use the Newtonian theory. So Newtonian theory is only applicable when the velocities that we are considering is very, very small or it is insignificant compared to this absolute velocity lambda. So then we can obtain it. And in relativity theory terminology, we say that if any object has velocity much, much less than the speed of light, then there is no need of considering the relativity theory. Newtonian theory is sufficient. But if the speed is comparable to the speed of light, then we must have to take into account of the relativity theory. So that's the beauty, and from there we can derive the Galilean transformation. Okay. So now I am coming gradually to an geometric notion. Okay, we have considered it. And what's the geometric notion, or what's the, because we are still in the Euclidean geometry. So that's the notion that we are now talking about. So for that, I am again considering a quadratic form, a quadratic expression that I termed as a square, which I called as x square plus y square plus z square minus lambda square t square. Now, this is something like that. In four-dimensional space, I have 2 points. One point is 0, 0, 0, 0 origin. Another point is x, y, z, t. And I am considering the space-time interval. According to the definition of the space-time interval, the space-time interval will be like this: x square plus y square d square minus lambda square t square, and that I called x square. And if you calculate, if you check that, according to Lorentz transformation, this is invariant. Invariant means if you calculate in x dash frame, that means if I calculate x dash square plus y dash square plus z dash square minus lambda square t dash square. So if I now try to calculate this quadratic form, and I use the Lorentz transform, so I know about x dash, I know about y dash, z dash, and t dash in terms of x, y, z, t. I just substitute them, and I make some algebraic simplification. If I make some algebraic simplification, I see that it turns out to be x square. That is x square plus y square plus z square minus lambda square. So it is invariant under Lorentz transformation. Now, this is invariant. Okay, what's the sign of it? It can have three signs because it is a positive indefinite quantity. So it can have sign positive, negative, or even it may be zero. Now, what it implies? If it has the sign positive, it has the sign positive means the velocity will be greater than the velocity of lambda. If it has the sign negative, it means that the velocity is less than lambda. And if it is zero, then it implies that the velocity will be equal to lambda. So that's why I have written that. Now, is it possible that a square can have all these three signs? No. A square cannot have all these three signs. Why? Because if we go back to the Lorentz transformation, you see that in Lorentz transformation, the relativity factor gamma is there. Gamma is 1 by root over 1 minus v square by lambda square. So if v is greater than lambda or equal to lambda, you cannot have this Lorentz transformation. So you cannot have velocity greater than or equal to velocity. You must have velocity less than lambda. Then Lorentz transformation is well defined. So here I am getting the three quantity, a square will be greater, less, or equal to lambda, and that gives us some absurd result that v is greater than or equal to lambda. That is not possible. So only possibility is that v is less than lambda. So our only realistic possibility is that a square should be less than lambda, less than zero. So that case we have to consider. Now, can we think over it now geometrically? So I think over that a square equal to 0. So I start with this case. So that means that x square plus y square plus z square minus lambda square t square equal to 0. What it implies? So I have now in the fourth dimension. So in fourth dimension, what it implies? So before that, for simplicity, I start with the 3 dimension. So in 3 dimension, I can consider x square plus y square minus z square equal to 0. What it implies? In 3 dimension, so I have 3 space coordinates. If I have a surface which is given by x square plus y square minus z square equal to 0, what it implies? Now it implies a cone. How we can identify that? Because if you visualize that in 3 dimensions, suppose z axis is vertical and x, y are on the horizontal plane. So if I consider a certain z, suppose z equal to z0. So if I fix z equal to z0, what I get? I get x square plus y square equal to z naught square, because I have the equation x square plus y square minus z square equal to 0. So then I have the equation x square plus y square equal to z naught square. What it implies? It is a circle. So I have a circle of radius z0. Now I increase z0. So I get another circle of larger radius. If I decrease or if I descend along the z-axis, I get a circle again of smaller radius. In that way, I have infinite number of circles having radius gradually becomes more and more as we go towards the positive direction of the z-axis. So I am getting a cone. So in 3 dimension, that is a cone. So same analogy here in the 4th dimensional space-time. Here also we have a 4th dimensional cone. So it is it is not possible to draw that 4th dimensional cone. We have to visualize. Now, how these cones are constructed, that you can see. So I choose suppose time axis is vertical. So you have to imagine. So I choose a particular time, t equal to t0. So at that time, the equation gives us x square plus y square plus z square equal to lambda square t0 square. So it's the equation of a sphere of radius lambda square t0 square. So that's the equation of a sphere. Now, if I increase t, I get a larger sphere of larger radius. If I decrease time, I get a sphere of smaller radius. So in that way, I have several spheres constructed one by one with increasing radius. So that's also a cone in 4 dimensions. We have to visualize it. It is not possible to draw that. So that cone in relativity theory is termed as light cone. Why that is termed as light cone? Because on the surface of this cone, the velocity is equal to the velocity of light. So velocity is identical to the velocity of light. This implies that that's why they are termed as the light cone. But here, as we are not talking about the velocity of light, we term that null cone. Null is a square equal to 0 that we are considering. That's why we called it as the null cone. But it has null terminology. It has some other aspects for that's why we are calling it null. But I am not going into that. So in any case, it is known as the null cone. Now, I have now 3 distinct regions. One region is inside the cone, other region is outside the cone. So this is the inside cone, this is the outside cone, and this is the surface of the cone. And how we can identify? Inside is identified by a square equal to 0, outside is identified by a square greater than 0. And surface is identified as a square equal to 0. Now, this cone, it is consists of 2 cones. Now, this is in the forward direction of time, this is in the backward direction of time. Now, this is known as the past light cone, this is known as the future light cone. Now, we have simply talked about the future light cone. So, a square less than 0 is realistic one because here velocity should be less than lambda, v should be less than lambda in this region. And here on the surface, v equal to lambda, and here v is greater than lambda. So, all realistic region, realistic events which are happening with velocity less than lambda, they are confined inside the cone. And all other impossible things are outside the cone. So now you see that we are in a very peculiar situation because in Euclidean geometry, that is in Newtonian theory, we are in the Euclidean geometry where space is totally unbounded and we can move anywhere from minus infinity to plus infinity. There is no restriction of moving from one place to the other. But in relativity theory, we have a severe restriction. We are confined only inside the cone. We cannot go anywhere outside that. So for every observer, observer is sitting here and they are confined to observe only all those natural events which are happening inside the cone. So that we are very much in a restricted region within the cone. So you see that there is a huge drastic change in the mathematics, in the geometric formulation of this. Now, but we simply changes the one thing by which we have so much of geometry changes drastically. What the simple change? Because instead of 3 dimensions, we are now considering only 4 dimensions because we are considering space-time. So it's 4 dimensions. So that we are considering dimension is not the matter because in Euclidean geometry, we can have any dimension. But one thing is that here all the 4 dimensions are not space. 3 dimensions are space and 1 dimension is time. And only thing that we have taken into account is the irreversible character of the time coordinate. And as a result, we just tilted or we just make a very slight modification of the Euclid's postulate that length invariance now becomes space-time interval. We just put a minus sign in front of dt square. And we mathematically argued that that is correct because that can identify the time coordinate so that irreversible character of time coordinate can always be maintained in any coordinate transformation. So this simple small change put a drastic changes in the geometry. And we are now no longer in the Euclidean geometry. What type of geometry now we have? This geometry is usually known as pseudo-Euclidean geometry that is more in abstract sense, but in more popularly, it is known as the Minkowskian geometry. Because before Einstein formulated it, Minkowski has already developed this geometry. Because he just deviates from the Euclidean geometry with a minus sign, and he examined what type of geometry I am getting. So that type of geometry was already started by Minkowski. So that's why this geometry is known as the Minkowskian. So we see that by starting with the Euclid's postulate and just modifying in a very small slight with a sign, just to incorporate the irreversible character of the time coordinate, we have changes not only the physical theory, that means we have changes from Newtonian theory to the relativity theory, Einstein's relativity theory, but also we changes the geometry to a great extent. We are no longer in the Euclidean geometry, we are now in the Minkowskian geometry, which is in some sense it's a bounded geometry, though the cone on the upper side is unbounded. But we are always restricted inside the null cone that we are considering. So geometry has totally changes, physics has totally changes. Now I consider what other changes it has and what are other consequences it has. Now, first of all, I started with that addition. Now I shall show is that addition has any interrelation with this geometry. So now I shall show that the algebra, the usual algebra that we consider, that means the usual addition rule, that is also not true here. And the addition that we have started with, that is the real addition here in special theory of relativity. So algebraic structure also changes. So that we shall have to consider. So that I mentioned that is the Minkowskian geometry. Now, before going to that algebra, I just say very briefly, before going more details into these geometrical notions, what this algebra is, that. Now, here you remember that I have putting a plus b equal to a plus b by 1 plus ab by lambda square. Now, I put it, suppose I have two frame of references and relative to a fixed observer, they are moving with velocity u and v. Then what will be the resulting velocity of those two particles? If I calculate the resulting velocity in using this relativity theory, now first of all, how you can get the relative velocities? Now, the relative velocities you can go, just I say in that way, you start with the Lorentz transformation. You have this transformation equation. I am not going into so details of those calculations. I just giving you the flavor how you can of yourself can do those calculations. So I have this transformation. So suppose I have a particle which is moving with velocity u. U means dx dt, dy dt, dz dt in S frame. So in S dash frame, it has the velocity u dash. So that is dx dash by dt dash, dy dash by dt dash, dz dash dt dash. So this is the velocity in S dash frame. Now, is there any interrelation between, suppose I call it ux, uy, uz and ux dash, uy dash, uz dash. Is there any interrelation between them? You can very easily find that. Because whenever you calculate ux dash, this is ddt dash of x dash. Now ddt dash of x dash, that you can find out. Now t dash is this. So dt dash, I can put gamma into dt minus x into dx by lambda square. Similarly here, dx dash, I can put gamma into dx minus b into dt. So I can very easily calculate dx dash by dt dash, that means ux dash in terms of ux and v. And you can calculate that. Similarly, other component of the velocities, you can find that. So using that, you can find out the transformation relation between the velocity components. So from there, you can calculate the resulting velocity. Suppose a particle is moving in S dash frame with a velocity u dash along the common x dash axis. And the same particle is observed by the S frame with a velocity u, then you can find out the relation between u and u dash. The relation that you get is same as that addition rule. That means u will be equal to u dash plus v by 1 plus u dash v by lambda square. That simple result you can get from easily there. I will not go into details of those, and those are already there in the relativity. So that's why we have omitted those. Only things that I put here are those unconventional things which are not there in the text. So you can find out that transformation, that relative velocity, and that you see that always follows that addition rule, which I have given as the addition rule there. That means u will be equal to u dash plus v by 1 plus u dash v by lambda square. So interesting part is that the result that we have mentioned, that if I add two velocities, that will be always less than lambda. If I add one velocity with lambda, that will be equal to lambda. So by addition, we can never get any velocity greater than lambda. So if I have two velocity less than lambda, then I always get a velocity which is also less than the velocity lambda. So if by addition we have a velocity which is less than lambda, then the Lorentz transformation equation, whatever number of frames we are considering, is always retained, because we cannot have any velocity greater than lambda. So in every sphere, we always get velocity restricted by, or it has an upper bound lambda. So this means that Lorentz transformation is always valid. So what we see that just by what I say, the small change in the time coordinate, that means due to the irreversible character of the time coordinate, all the three basic structures, the algebraic structures, the geometric structure, and the physical theory, all three changes by this, simply starting with the Euclid geometry. So we have no notion of any physical theory. Just starting with the mathematical theory, we can develop this theory of relativity as Einstein was doing. Not only that, we have something more in this theory compared to the special theory of relativity. What is something more? Because now here, they are restricted only with the velocity of light. Now, what happens if one day we find a particle which has a velocity greater than lambda, greater than the velocity of light? Now, so far today, we don't have any velocity, any particle which has a velocity greater than the velocity of lambda, a velocity of light. But who guarantees that in future we are not getting any particle which has velocity greater than c? So in that case, relativity theory will break down. Then what will happen? Because you know that 4 or 5 years ago, one fine morning, we all see in the newspaper that Einstein's relativity theory has proven false, has been wrong. Because in the sun, and in the Large Hadron Collider, there was an experiment performed where they got a particle, that was known as the GOT particle, but that is actually the Higgs boson, and they calculated the velocity of that from the observation, and they found that that velocity is greater than the velocity of light. So Einstein's relativity theory no longer valid. So that's why that is the newspaper headline. But immediately after that, they recalculate that and they found the error, and ultimately that velocity is not greater than the velocity of light, so Einstein's theory survived. But we don't know that in someday in future, there we cannot get a particle which has the greater than the velocity of light. So if one gets that, what will happen? So in that case, relativity theory will be installed. But if we formulate in that way, here I have also a limitation. We have a upper bound lambda, but we have no restriction. Lambda is simply a real, positive real number. But we have not mentioned anything else. So if you get a velocity, say twice c, a particle with velocity twice c, I always choose lambda greater than twice c, because it has no restriction, it has no limitation. So I can choose lambda to be as large as possible, so that all particles that we have so far, we know all velocities will be less than lambda. So in that sense, Einstein's special theory of relativity will always be there, whatever velocity we find, and in future also, so that its relativity theory is there. Now in this context, I just say, so far there are 4 basic fundamental theories which are beautiful, but among all other theories, only special theory of relativity is flawless. It has no drawback so far. So that is the theory. Okay, so now for the, I shall go further into the geometric ideas. So now I have 4 dimensions of space-time. So in these 4 dimensions of space-time, I consider a vector. So in 3 dimensions, I have 3 components. Now I have 4 components. A0, A1, A2, A3. A0 is the time part component, and A1, A2, A3 are the 3 space components. So that I call the 4 vector. Now, if I calculate the norm, that means the length square of this vector, if we calculate, so algebraic structure that I have formed, that's a vector space. That vector space, now I have a metric, and that according to that metric, I can calculate the norm square. Now, that norm square turns out to be this, minus A0 square plus A1 square plus A2 square plus A3 square. So that's the norm square. And this norm square is not positive definite. So that is also a very unusual situation, because we always know that length of a vector is positive. That length square is always positive, but here it is positive indefinite. Again, it can have 3 signs. It can have positive, negative, or 0. If it is positive, it is known as space-like. If it is negative, it is time-like. And if it is 0, it is known as the null vector. Again, we have another unusual thing we come across, null vector. If norm square is 0, we termed as null vector. We are not at all aware of this null vector. We only know 0 vector. A vector having all components 0 is known as null vector. But here is known as the 0 vector. But here we see that it's a null vector. Null vector means here all the components of the vector are non-zero, but its norm is 0. So that's why it is known as the null vector. So this type of vector is not possible in Euclidean geometry. So in this geometry, we have the notion of null vector. And here I just mentioned that this null vector is very, very important. It has a very crucial role in studying the general theory of relativity. Einstein's general theory of relativity, where also this null vector has a very active role there, and it has a very peculiar property. Now, one simple property I just mentioned, that these vectors can maybe space-time. Okay, sorry for the intervention. Some internet problem is there. So these null vector. So if we have a vector, suppose I have a surface for which this null vector is the tangent. Then this null vector is not only the tangent, it is also the normal to that surface. So a same vector which is simultaneously tangent and normal to a surface. So that we can't imagine usually in the Euclidean geometry. But it is true in this pseudo-Euclidean geometry, or more specifically in the general theory of relativity in the Lorentzian geometry. These null vectors have those properties that suppose we have a surface for which this null vector is tangent, then that vector is also normal to that surface. So there are other peculiar properties that there, that I just state only this one, which is very interesting. So this is one character, that so here the norm square of a vector is not a positive definite, And if non-square is negative, that is time-like. Time-like means those vectors lies inside the cone. So they are physically realistic vectors. And space-like means those vector lies outside the surface. So that is space-like. And this is time-like region, and here the all time-like vectors lies. And these null vectors, they lies on the surface of the. So all this, because that's why this is known as the null surface. And that's why this cone is termed as the null. Because all null vectors, they constitute this surface. So that's why this is known as the null surface, and that is known as the null. So that's the reason why this is known as this. Okay, so now I have another notion. So that is also another interesting issue that I shall talk about. Now at the starting, we said that as the velocity of light should be invariant by observation. So Einstein speculated that time cannot be absolute, time should vary from one frame to the other. So time is a relative concept. So time is a relative concept, and that's why we are considering space, four-dimensional space-time. So time varies from one observer to the other. Though time is a relative concept, but still interesting is that we can formulate a notion of time that is invariant, that is same for all observers. How we can define that? Now here I have the space-time interval, dA square equal to this. Now you note that I divide it by lambda square and with a minus sign. So minus dA square by lambda square. And here you can think that this is 1 minus dx dt whole square, dy dt whole square, that is the velocity square, u square. So 1 minus u square by lambda square. So here you see that this is a purely a number, and here it is dt. So it's a dimension of time square. So that's why I call this the d tau square. So it has tau as the dimension of time. So d tau square I have given like this. Now here you see that dA square is an invariant quantity. We see that it is invariant under Lorentz transformation. So it is invariant. So dA square is invariant. Lambda is constant. It doesn't change. So this quantity is an invariant quantity. If this is invariant quantity, d tau is an invariant quantity. So if I calculate tau, which is this, it's an invariant notion of time. And that is known as the proper time. So that is the beauty of the relativity theory. Though at the very beginning we start with the relative notion of time, time cannot be identical for all observers. But still in relativity theory, we can have a invariant notion of time, and that is known as the proper time. So proper time is the invariant notion of time that we can introduce here, so that we have this invariant notion of time still remain in the relativity theory. Now, can we utilize this proper time in a very nice way? Yes, this has a very nice application. What's the application? Now we are considering a four-dimensional space-time. That four-dimensional space-time is characterized by lambda t and xi. That means all have the same dimension. All has the dimension of length. Lambda t is the first coordinate that we have written as the x0 there. And then x1, x2, x3. Instead of xyz, I write x1, x2, x3. So now I have four coordinates. And that I have termed as x mu. So x mu has the four coordinates. So this is the x0 and this is x1, x2, x3 that I abbreviatedly written as xi. So I have written that. Now I differentiate with respect to the proper time. So I calculate dx mu d tau. So that I call four velocity vector, because it has four components, four velocity vector, and that I denoted by capital U. So it's a four velocity vector. Now, what are the components of this four? I just simply calculate this. If I calculate this four velocity vector, you can see that that comes out to be lambda in vector into gamma. You can very easily, using Lorentz transformation, you can calculate this. And using the notion of time, d tau related with dt in that form, so that you can get this, and gamma is the relativistic factor like this. So u mu, you can calculate like this. So u mu is this. Now I calculate the norm of this. If I calculate the norm of the vector, it turns out to be minus lambda square. So it's negative. It's a time-like vector. That means it's a physically realistic one. First of all, u mu is a physically realistic vector. It's a time-like vector. And second interesting property is that its magnitude is constant. And its magnitude is lambda square. What it means? If its magnitude is constant, what it means? Now, in every book, I find that this means that it's a time-like vector of constant magnitude and such that they have mentioned. But they cannot interpret it. I think it has a very, very nice and useful interpretation. Now you imagine a four-dimensional space-time, three space coordinate that I put simply as a, now I imagine just as a 2D diagram. In 2D diagram, I identify one direction as the space direction and the vertical direction as the time direction. So in vertical and one horizontal is for space and vertical is for time. So it is very easy to visualize in 2D. So now I have 2D diagram. So in 2D diagram, I have a particle moving and that particle has the velocity, this u mu, capital U mu, that is 4 velocity. Now this 4 velocity has two components. These components are lambda and u. These two into gamma. So these two components. So particle is moving with these two velocities. So here you see that whatever be the particle, its resulting velocity is always lambda square. It's constant. So resulting velocity is always constant. Every particle has constant velocity and that velocity is the absolute velocity lambda. So if you think about in terms of the velocity of light, you see that whatever particle in these two dimensions has velocity of light, if you consider in the velocity of light. And what it implies? The resulting velocity means it has component along the space direction, it has component along the time direction. So now every particle has two components of velocity. One component of velocity is along the time direction, another component of velocity is along the space direction. But the resulting velocity is always constant and that is equal to lambda square. And that is equal to, or rather we can say it as c square, that absolute velocity. So in this picture, I don't know what space I can say. The space, I simply call it as a 2D plane. In the 2D plane consists of space and the proper time. In this plane, everyone is moving and everyone is moving with that absolute invariant speed. If I call it the velocity of light, everyone is moving with the velocity of light. And every particle, although every particle or every identity are not identical because they have not identical components along the space direction and the time direction. But the sum square, that is always equal to c square or lambda square, whatever you are saying. So in that way, every one of, whether they are human or any particle or whatever may be, everyone is moving and they are moving with the resulting velocity of this absolute velocity. Now, suppose I am sitting here in the space direction. I just sitting. So then how? I am moving with velocity of lambda or I am moving with velocity of c. How we can interpret it? We can interpret it that then along the space direction I have no velocity. All my velocity is along the time direction. So my time is only changing, but space is fixed. So that is my fixed position. So that is my rest position. So whenever I am in the rest position, then I don't bother about the relativity theory. So I am in the Newtonian theory. So in Newtonian theory, time is changing. So if there is a natural question, what's the velocity with which time is changing? Time is changing with this absolute velocity. Absolute velocity, if you call it as lambda, or if you call it the velocity of light, with that velocity, time is changing. But if you move with a certain velocity, then that velocity has the component, so absolute resulting velocity is c. So its component in the time direction now reduces. So time no longer moves with velocity c. That's why time gets contracted or time gets slow. So that's why in relativity theory, a moving observer's clock gets slow. So time gets slow when you are in moving. If you are fixed, then Newtonian theory, time is moving with this absolute velocity. So that is another geometrical interpretation of special theory of relativity. It is a very beautiful interpretation and it is very easily understandable in terms of usually in the school level mechanics or whatever you can say in geometry or mechanics. In terms of that, you can see that relativity theory is nothing but I have a two-dimensional picture. One dimension is along the time and another dimension is space, and whatever notion you are talking about, I can explain it this. Lastly, I just mentioned that, what about the light? Experimentally, we see that light is moving with velocity lambda or with velocity c. Then which direction it is moving? Light is moving purely in the space direction. It has no component along the time. So relative to light, time is fixed. Time doesn't change relative to light. So that's why one can say that light is ever young. That means the absolute velocity that we are considering relative to which time is totally fixed. So in terms of the light, if I say light is ever young, its time or its age never changes. So it always remains young. So that's the notion, or that's the very special character of light we can introduce in terms of special theory of relativity. Now I have only about 10 minutes. So for that, I just briefly say about the general theory of relativity. Now, what changes we need about the general theory of relativity? Now, about the general theory of relativity, I just say that in general theory of relativity, in the earlier slides, I just mentioned that we are talking about the linear transformation. So if I go over to the nonlinear transformation, we get it. But how Einstein developed that? Einstein developed, so for special theory of relativity, he introduced one more postulate, that is the invariance of the velocity. Now, when he introduced the general theory of relativity 10 years back, after 10 years, then he introduced one more postulate, and that is known as the equivalence principle. And that equivalence principle has an immense physical and geometrical meaning. What physical meaning it has? Physically, this equivalence principle means that equivalence between any gravitational field with any accelerated frame. In other words, we can say that you give me any gravitational force, that force is always equivalent to some accelerated frame. So any accelerated motion is always equivalent to some gravitational force. So that's the equivalence between gravity with some accelerating frame. So that's the physical notion of equivalence principle. And what's the geometrical notion of equivalence principle? Now, starting from this idea that any accelerated frame is equivalent to any gravitational field, you can see that the geometry changes to a great extent. In special theory of relativity, we are switch over from Euclidean geometry to pseudo-Euclidean geometry or Minkowskian geometry. Now we are totally out of the Euclidean geometry. We are now in a curved geometry. And now we are in a curved geometry that is known as pseudo-Riemannian geometry. There was a curved geometry before Einstein that Riemann was developed, that was known as the Riemannian geometry. And in Einstein general theory of relativity, it was slightly deviate from the Riemannian geometry, and that was known as the pseudo-Riemannian geometry, or sometimes it was known as the Lorentzian geometry. So that geometry is again distinct from the Euclidean geometry. So equivalence principle also demands this. And not only that, there is a nice equivalence This equivalence principle gives a nice equivalence between this geometry and physics. Though equivalence principle first gives a very nice equivalence physically, that gravity with the accelerated frame, and then gives a nice change in the geometrical aspect. That means we are now in the pseudo-Riemannian geometry or Lorentzian geometry. But then Einstein also put forward to give a nice equivalence between these geometrical aspects and this physical aspect. How you give that equivalence? He gives the equivalence in that way that if you give me a gravitational force, then I can say that what will be the influence of this gravitational force on this geometry. How you can give that? By determining the curvature of that space-time. So curvature of the space-time always dictates the amount of gravitational field, or vice versa, the gravitational field dictates what will be the curvature of the space. How much the space will bend, that will be dictated by the gravity theory. So physics and geometry, they are interrelated, and that is Einstein's equation for gravity. In Einstein's equation for gravity, if you just write down that equation, you see that on the left-hand side, it is purely geometric. It is purely characterized by the curvature of the space-time. And on the right-hand side, it is nothing but the gravitational force. Due to that gravitational force, what will be the curvature? These two are nicely interrelated. So that's the basic idea of Einstein's general theory of relativity. So geometry has changes to a very great extent, and the conventional idea of gravity of Newtonian theory is totally changes here. And here we have the equivalence principle that gravity and accelerating frame, they are at some point will be equivalent. So these are the two important notions of Einstein's general theory of relativity and coming from the special theory of relativity. So I think I stop here. It is almost 6. So if there are some questions, I think I should answer, and then the other talk will be started. So is there any questions? So I try to answer them. Thank you all for your patience for listening to me. Thank you all.
Thank you very much, sir, for such a full lecture. In simple words, the way you made us understand fundamental concept of Einstein's special relativity in the context of Euclidean geometry, the way the Lorentz transform explained only from geometry ground without considering physical theory is very interesting and enlightening. You also, in a simple manner, link the pathway of general relativity from by adding equivalence principle. Thanks again, sir, for your magnificent lecture. Now we shall take few minutes for discussion. Are coming up. I shall request Miss Anesha Shento to start the question and session. Anesha, please.
Thank you, Dr. Vishash Madam. So let us take few questions from our participants. So first, am I audible, sir?
Yes.
Okay. So what is the difference between special theory of relativity and general theory of relativity?
Yes, I have already mentioned that in special theory of relativity, I can say in geometrically and physically. In geometrically, I can say that in geometry is totally different. In special theory of relativity, we have the Minkowskian geometry, and in general theory of relativity, we have the Lorentzian geometry. So geometry is changing. And in physical form, we can say that whenever we consider in we know that in nature there are 4 types of forces. And if gravity is not considered, then we have the special theory of relativity. But if gravity is introduced, then we have the general theory of relativity. So absence of gravity implies special theory of relativity, and if we include gravity, then we have the general theory of relativity. Okay.
Thank you. Next, how Newtonian theory related to Einstein field equation?
Einstein field equation means in general relativity or in special theory of relativity?
In both, maybe.
No, in Newtonian theory, if you consider, I have mentioned that in Einstein's special theory of relativity, only the basic things are the Lorentz transformation. From Lorentz transformation, everything is derived. So if I call it in terms of the velocity of light, c, then if c goes to infinity, then everything of special theory of relativity switch over to the Newtonian theory. So that's the idea. That means whatever velocity you are considering, if it is insignificant compared to the velocity of light, then you are in the Newtonian theory. But if it is comparable to the velocity of light, then you have to take into account of the special theory of relativity. So that's the interrelation between the Newtonian theory and the special theory of relativity. And Newtonian theory and Einstein general theory of relativity, whenever you make a comparison between these two, then you have to talk about the Newtonian gravity theory and the Einstein's general relativity, because it is totally related to the gravitational field. Here you can see that if the gravitational field is very, very weak, then it is mathematically, it can be shown that Einstein, the field equation of Einstein's general theory of relativity reduces to Newtonian theory, where the equation is Poisson's equation. So it is related, just reduces to the Poisson's equation. So that's the relation between these two theories.
Next, if DSS square is of signature -2, then what will be the structure of light cone?
Same. Structure of the light cone doesn't change with the signature. If the signature is +2 or -2, the whole relativity theory does not change. It will remain same, only you have to take into account of the sign. Here I say that if ds square is less than 0, then it is time-like. Then we say that if ds square is greater than 0, then we say it time-like. Okay, only the sign change will be there. Otherwise, it is otherwise everything is same. So theory, relativity theory does not depend on the signature of the space-time, whether it is time-like or whether it is +2 signature or -2 signature.
Okay. Next one. Is space and time are both bounded on Minkowskian geometry?
No, both are unbounded.
What will be the time-like vectors and space-like vectors in space of signature -2?
Signature, it doesn't depend on the signature. Only thing is that if it is, I have mentioned signature +2. That's why for time-like vector, non-square is negative. If it is signature -2, then non-square will be positive for time-like and other for the space-like vectors. Only these changes will be there, but no other character, geometric or physical character will change for change of the signature. Okay.
Okay, sir. Next one. Is light has mass?
No, light has no mass because it is massless particle. So how it can have mass? Because hypothetically we cannot introduce mass. Mass is not so easy to introduce into any object, because according to Einstein's special theory of relativity, E equal to mc square. So if you introduce just 1 gram of mass, so you need the energy of c square amount. So who give you this huge amount of energy? So it is not possible. You cannot introduce or you cannot destroy any mass, because that needs a huge amount of energy. And that is the fundamental theory for atom bombs. Because there in somehow from the atom you are just extracted a small amount of energy. And due to this small amount of mass, and due to this small amount of mass, there is a huge amount of energy that is coming out. And that explodes enormously. So it is not possible in nature. So light particle has no mass.
Okay, sir. Next. Actually, you have said that it has no component in the time axis. Mass has no component in the time axis.
Now, mass has no component, I have not mentioned. Only thing that I mentioned that it has no component along the time axis is the velocity of light. Light particles, that is photon, they are moving only along the space direction. So all its component of velocity is along the space direction. It has no component of velocity along the time direction. So that's why for light particle, time doesn't change. So if time doesn't change, is time remains same. So that's why it is sometimes people say that it is ever young. Its age cannot change. Because for all other particles, all its component is not entirely along the space direction. It is in inclined way, just two vertical lines. So velocity is along any inclined direction. So it has one component along the vertical direction, one component along the space direction. So no one is equal to the velocity of light. So that's why as it has component in both ways. So time also changes, space also. But for light, only space changes, time doesn't. So that's the peculiarity of only of the light particle.
Okay, sir. Next, if for an moving observer, time becomes slow, then is time travel possible?
Mathematically it is possible, but physically there will be some problem, because if you go for time travel, then you have to go for the past. Also mathematically also there is, because then from future to the, you have to go to the past. So you have to cross some point. So where there should be some discontinuity. So that's the mathematical difficulty, and physical difficulty is there, that from future to the past, whenever you are traversing, then you have to move with a speed equal to the velocity of light. And that is not possible. So that's why time travel, theoretically, mathematically, it is okay, but practically, so far it is not possible. People are trying in different way, but no one has succeeded physically. That I must say. So that's why time travel is not possible.
Okay.
But it's a very interesting issue. People can think over that. Okay.
Next, sir, is it possible to get a particle which has velocity faster than light?
No. So
If
far,
yes, oh, okay.
so far it is not. But I have mentioned that if it has a velocity greater than c, then I consider lambda, because I can deduce relativity with this lambda. So I choose lambda, whatever velocity you are thinking about, I choose lambda larger than. So velocity larger than something is not needed here, because lambda is arbitrary. So that's why that question doesn't arise here. But if you maintain it or restrict it to the velocity of light, then there will be problem.
Okay. Next, does tidal acceleration results the breakdown of principle of equivalence?
Not in that sense, but sometimes it breaks the equivalence principle, but in a different notion. That notion is that not like that. There the geometry totally changes, because we have two different directions of acceleration, and then the resulting acceleration will be a little bit complicated. So in some sense, it breaks the equivalence principle, but that is not important, because there the gravitational force which breaks the equivalence principle is so small or so negligible that Einstein's relativity theory does not care for that. So because it's a very weak, so Newtonian theory is sufficient. So there is no need of considering the general theory in that case. So that's why that breakdown of equivalence principle is not very much important in that sense. Okay.
Okay. Sir, another question. Would you please explain a bit about null hypersurface?
Null hypersurface is a surface on which normal is a null vector. Null vector I have defined. So if the surface has a normal vector, which is a null vector, then that surface is known as a null hypersurface. Okay, it's a geometrical notion, and that definitions are there standard in differential geometry. But loosely, it is the definition you can consider. There are formal definitions also, but I am not going into those. But loosely, we can say that the surfaces having normal as a null vector are termed as the null hypersurface.
Okay, sir. Last one. How special theory of relativity do deduction of time dilation and length contraction?
Length contraction, yes, that you can mathematically. Time dilation I have already mentioned. And according to that diagram, 2D diagram that I last mentioned, if velocity along the time direction reduces, not c, it reduces, then time will go slow. Previously, it is going with velocity c. Now it is going with velocity less than c. So time will go slow. That is the time dilation. And length contraction also in the similar way. If you move with a faster velocity, then length will appears to be contracted in that way. And those can be mathematically derived from the Lorentz transformation. But this 2D diagram is very useful for explaining or understanding those ideas. So that's why I at the end mentioned it. But unfortunately, these things are not there in the books. That's why people sometimes get stuck to understand this relativity. They seems to be that it is more abstract, but it is not at all abstract. It is very easy and it is very lucidly you can thinking over with the usual concept that we have. Okay.
Okay, sir. Thank you for such interactive session. Now I am requesting Madam for take up the next session.
Okay. Thank you all.
Thank you very much, sir, for considering us, for your valuable time. So we have to now move on to the next lecture. If you have any more question related to this first lecture, you can drop your question in our discussion forum. We can convey your questions to a speaker. So there is no problem regarding this. So let us move on to the next lecture. Our second speaker is Professor Abhishek Adhikari. He is from Mathematics Department of Presidency University. He is also very popular and well-known figure in mathematics community of India. He has published more than 50 papers in reputed international journals, conference proceedings, and contributed volumes. He is on the editorial board of several journals. He is also investigators of various sponsored research projects funded by different agencies like DRDO, DST, DST South, DST, FIST, etc. And he's also guiding number of PhD students right now. His research interest includes applications of algebra, graph theory, cryptography, crypto analysis of stream and block ciphers, secret sharing, DNA cryptography, visual cryptography, image encryption, wireless sensor networks. I request Professor Adhikari kindly to deliver his speech. His title of the lecture is Introduction to Mathematical Aspects of Cryptography through a Mathematical Tool. Professor Adhikari, please.
Thank you very much for this nice introduction, and I would like to thanks to the organizer for giving me an opportunity to have kind of interactive session with all of you. And of course, good afternoon to all of you. Let me first share my screen. And am I audible?
Yes, you're partially
Yes, sir.
audible.
Audible, you are.
You're audible. Please, Abhishek, please carry on.
Okay. Is all the tabs are also visible? This one also visible?
Yeah, we
This
can see your screen also.
Yes, it is visible.
okay. So all the tabs are working fine. Okay. So the title of my talk is Introduction to Mathematical Aspects of Cryptology Through a Mathematical Tool. So I think by now on, with this lots of applications of computer science as well as lot of attacks from different agencies, different countries, cyber attacks mostly. We are now quite adequate or quite, we know the term about cryptography. So in my talk, I will try to highlight how mathematics, mostly number theory, abstract algebra, play an important role in having this kind of cryptographic schemes. In my talk, I will basically try to use some of these packages. So it's a mathematical tool, we can say it. It's a Sage Math. If somebody is there from Calcutta University, in their undergraduate syllabus, the Sage Math has newly introduced from recent years. So we will show how the Sage Math could be useful. So it's nothing but a package like MATLAB or Mathematica, but the advantage of this is it's a free open source software. So anybody can use it, and the use of using this, you can do not only good for teaching, but it's also good for research. So I will show some of the very exciting results using that kind of mathematical tool. Okay, so when we go just after our 12th standard, when we go for our undergraduate studies, in abstract algebra, usually the first thing that we encounter with, or the first major thing that we encounter with, is the group theory. So we all know that group theory has some definite properties. It satisfies some few of the axioms. So mostly, if we don't consider group to be a kind of binary composition from G cross G to G, satisfying some properties, if we consider a binary composition or operation, then usually we don't think about this closure property, because from the definition, it's already there that closure property is already involved within that. So we don't need to consider about closure property. Otherwise, we have to consider the associativity, identity, and inverse property. And these two guys, this Jordan and Dirac, they are considered to be the forefathers for having this axiometric definition for group theory. So we call it axiometric definition because it follows some axioms. When we go a little deeper of this subject, so we usually encounter with Lagrange's theorem, abelian group, normal subgroup, Cauchy subgroup, or Cayley's theorem, Cauchy's theorem, etc. Now, if I ask you a very simple question, who invented Lagrange's theorem? A very quick answer would be certainly Lagrange's. And if I ask you who gave the name for abelian group, you will be certainly answering that abelian must have given this name, abelian group, after his name. But let me show you a kind of statistics. So just have a look at when Jordan and Dirac, they worked on this particular definition of group, it's around 1870 or 1882. Now I'm going to give you some of the sketch for Lagrange. So it's Lagrange. So Lagrange was with us from 1736 to 1813. So Lagrange's theorem, Lagrange actually died in 1813, much earlier than the definition of 1870 about group theory by Jordan. Similarly, if you look at Abel, so we usually think that abelian group actually came from the name after Abel. Yeah, it named after Abel, but Abel didn't give the name of abelian because he was there with us from 1802 to 1829. Similarly, it is assumed that the normal subgroup, that term usually coined or described by Galois, and he was also there from 1811 to 1830, much earlier than 1870. Similarly, Cayley or Cauchy, all of them, they actually worked in this area much before than the formal definition of group theory. So the question is, then how the name came? So it's actually due to Jordan, who mostly gave all the names. So he first started looking at who actually pointed out this concept. So Lagrange's or Abel, they actually at that time, the solving equations, for example, quintic equations, having the solution using the technique, normal technique, like for 2-degree curve, we have Sridhar Acharya, or for 3-4, we have Ferrari or Cardan's method. Now, what's about 5-degree and all? So can we have some method, general method for doing this? And for the first time, Galois and Abel, they independently proved for the first time that we cannot have a general method which actually contains, we call it charges and all. So they actually did it mostly on dealing with permutations and dealing with system of solutions and system of equations. During that time, they had this kind of concept, and based on that, Jordan, they actually came up with these names. So it's not all due to their names, but it's due to Jordan, who actually later on, when he established these results and all, he actually gave the name after their names. So we are thankful to Jordan. But when we go a little deeper of this, then we see that many of the big mathematicians, they work on it. And broadly speaking, this group theory can be thought of in from three different sides. For example, from set theoretic viewpoint, from geometric viewpoint, or from number theoretic viewpoint. So there were plenty of big mathematicians actually worked on this group theory, and now this group theory is considered to be an established subject, and it's considered to be a subject of our undergraduate, or sometimes at the level of 12 when they are preparing for the ISIE exam and all. So the question that comes to our mind, usually when I was doing my undergraduate level, the question that haunted me most was, are there any applications of this abstract algebra? Everything looks very abstract to me at that time. Then when we study a little bit more, from our very childhood, actually, the number theory also comes into picture, because from our very childhood, the numbers are play most important role in our life. For example, how many toys that I have, or how many chocolates that I am giving to others, etc. So this kind of things are we are very acquainted with from our very childhood. But among these numbers, few numbers play a more important role. For example, these are the examples of prime numbers. So this prime numbers actually plays an important role. And in our undergraduate studies, we also do have lots of studies and properties about this number theory. So let's just have a very brief look at the history of prime numbers. So you'll be surprised to know that the ancient Greek mathematician, they used to work with these prime numbers, and they knew lots of properties of prime numbers. For example, Pythagorean schools. So it was 500 BC to 300 BC. So it's before Christ. So it's more than 2,500 years back. They were interested in the numbers for this mythological reasons. Euclid, we all know about Euclid. So he was around 300 BC. So around 2,300 years back, he actually gave the idea, the formal proof that there exist infinitely many primes. And he used a very nice property by using this contradiction method. So now sometimes we use this property very frequently while proving something, that something, suppose we assume something, we know that this assumption is wrong, but after a few steps, when we find that some steps or some problem that comes, that the assumption that we assumed wasn't correct, then we say that, okay, the contradiction comes, and as a result, we have this proof. So for the first time, Euclid actually wrote it in his book, the method by contradiction. Not only that, he also gave a proof of fundamental theorem of arithmetic, which says that any positive integer, for example, greater than or equal to 2, be written as product of primes. And you know that this representation is unique in terms of some permutation and all. So that, just think about the year. So it was more than 2,300 years back, they actually dealt with all kinds of this kinds of numbers. But unfortunately, in the writing of Euclid, we couldn't find the process how to get prime numbers. He gave a lot of applications, or lot of, not applications, lot of properties of prime numbers, but he didn't give any idea how to get prime numbers. So it was for the first time in a written document, it was around 200 BC. Again, 200 BC, the Greek mathematician Eratosthenes, who actually using the sieve technique, who actually gave for the first time how to find prime numbers. Now think about all the time, it was more than 2,000 years back. Now, if you look at the history of number theory, then it was a very long, dark age. So usually we call it, in terms of number theory, we call it this as a dark age, when no significant result came into picture in terms of number theory. But suddenly around 1601 to 1665, Euler, this is Fermat for the first time came into picture, and he proved a lot of interesting, or he gave a lot of interesting results on number theory. So he was a kind of interesting character, and there were plenty of interesting stories and news are there uh, around his lifestyle. Okay, so I'm not going details about that, but after that, Mersenne and Euler, they came into picture and they gave also a lot of very interesting results. Now you can consider number theory is considered to be one of the established subjects, and it's considered to be a subject, as well as it has a lot of branches and many new subjects are coming up based on this number theory. So I'll just very briefly touch upon few of the very interesting problems of number theory. So that's Fermat's last theorem. So he actually gave around 1637. So it was Fermat who gave this. We all know the statement of this. So it says that if this, consider this equation, a to the power n plus b to the power n equal to c to the power n, and if a, b, c are all integers, and if n, the value of n is strictly greater than 2, then you cannot find a, b, c all non-zero solutions. That means you cannot find a, b, c to be all non-zero, which actually, or positive integers, non-zero positive integers, which actually satisfies this equation if the value of n is greater than 2. So you can think if n, the value of n is 1, then we can always find infinitely many such a, b, and c which satisfies these properties. But if n is 2, then also we can cleverly choose these values of a, b, c such that it could be a kind of length of the right angle triangle, then we could have some integers. But it says that if the value of n is greater than 2, then you cannot find non-zero positive a, b, c which satisfies this equations. So it was actually the problem he was, it's a kind of news, or it's a kind of story that Fermat actually was reading the book Arithmetica by Diophantines. So it was a copy of that book. So while reading or studying this book, he actually found this problem. And Fermat had a kind of peculiar habit that whatever he gets, he usually make a lot of notes on the margin of this book. So every book or every exercise book, he writes on the margin. So while reading this book, he got that idea about this statement, and he wrote this statement, and he told that I know the solution of this problem, but I don't have enough space on the margin, so I could not write the solution of this. So that's the end of the story of this problem. And later on, through his son, this problem came into the real world, and there the mathematician, they jumped into that problem, and it was a kind of division that many mathematicians, they thought that there could be a solution for this. That means Fermat was wrong, but there were plenty of mathematicians who thought that Fermat was correct. And we had to wait around for the more than 350 years, when at the end of 1994, finally Andrew Wiles, he proved the result that, okay, the Fermat was correct. That means you cannot find such ABC positive non-zero integers which satisfies that property. And there was again an interesting story about that. So in 1993, Andrew Wiles, for the first time, he was giving a lecture. So it was a kind of 3-day seminar by Andrew Wiles in Oxford. So there, when he was presenting in the month of June 1993, it was a 3-day lecture, and the title of the lecture was Modular Forms, Elliptic Curves, and Galois Representations. So it was going on, and the end of the seminar on the 3rd day, he actually revealed that at the end of his proof, he said that, okay, that's the end of Fermat's last theorem, because whatever result that I have proved, that actually imply that the Fermat's last theorem is resolved. So it was a like sensation, and all the mathematicians all over the world, they jumped into that problem. And he was famous, and many things, many awards he was trying to get. I mean, many people are proposing his name, and people are trying to understand how he did this. While trying to understand this problem, how he did this, it was really a very big proof was there. But while reviewing this paper, Andrew Wiles itself, he found that there was a mistake in his proof. So again, it was a dark time during that time. But fortunately, within around 9 months, he actually recovered the proof, and finally he presented the corrected proof, and that is considered to be the first correct proof of Fermat's last theorem. and then the rest is history. So now you can understand it was a very simple looking statement, very cute, innocent looking statement, but it took around 350 years to resolve that problem with a very deep study of mathematics with very deep results of mathematics. So that's a nice history about this problem. So again, we go into another very interesting, very cute conjecture. It was by Goldbach. Goldbach actually wrote this conjecture to Euler. So what it says that every even integer greater than 2 can be expressed as sum of two prime numbers. That means, say, whatever. So I will just try to explore it, or I try to explain it by using this mathematical tool. It's a Sage software. So it's a Sage Math. So it's a nice one, because by using this you can do lots of things. For example, while teaching, it helps us a lot. For example, it can give a demonstration about 3D images, not only 3D images. It's an example of sine 1 by x, how to plot this. So while teaching the students, sometimes it's really difficult to draw or to explain them very easily about some curves, because curve tracing is not that easy phenomena. So it requires a lot of practice, as well as it's a kind of art, we can say. But with the Sage software, we can very easily plot. So you can also plot by Mathematica or MATLAB, but I mean, it's really difficult for an institute to buy a licensed copy of it. So it's a free software, so anybody can use this. So this is the kind of animation about sine 1 by x kind. So it's sine a by x. So if you vary the value, we can explain our students that, okay, when it goes to the origin, then it behaves like very up and down motions, you can see. So it's a nice animation that we can make using this Sage, and you can make nice pictures, you can rotate things, 3D images, you can do lots of linear algebra like finding determinant, eigenvalues, eigenvectors, and all many things, integrations, while doing the derivative of things, or while teaching them with sequence, how it converges when you have less number of points, you say that it's quite had depth, but it's actually going towards 0. But if you increase the interval, then you can show that it actually nothing but goes towards 0. So that's the meaning of how it's tending towards, or summation, what is the meaning of convergent and all. So that could be very easily made. We can do lots of graph theoretic problems. For my research problems also, I sometimes write codes for Sage programming, which gives me lots of things very easily. So you don't have to actually quote many things, because most of the things are written. You just have to know how to use it, and it's a very good helps are there online. So if you just go into it, and then you will love it, I'm sure. Okay, so just I'm going to the Goldbach conjecture. So what it says, if you give any even number which is greater than 2, then it can be written as sum of two prime numbers. For example, if I put 100, then if I run this program, you see that 100 can be written in many ways, like 3 plus 97, both of them are prime, 11 plus 89, and so on. Now, may I request any of the participant in the chat box, can you please give me any even number, so that I can show you that how it's actually working. Or you can unmute yourself and tell me. Okay, I cannot see the chat box. Somewhere might be here. Okay, can anybody unmute and tell me? Yeah, any even number, then I can show you.
Hello?
Yeah, so any even number.
Okay,
Just
sir. Like 2222.
2222. Anything else you want? Any?
Someone asked 10,008.
Okay, first let's see how 2222. See, 2222, it would be difficult to understand whether the last one is prime or not, but believe me, they are primes. So 19 plus this. So there are many ways to write it. So all of them you can write it like this. Okay.
Okay, okay. So may I ask you some small answer
Yeah,
number
maybe that
like
would be easier
34?
for you
Yeah.
to check at least.
Okay,
So
thank you.
maybe 78, maybe say, let's see,
Okay.
78. So you can see that all of them are. this. Okay, but the point is, this Goldbach conjecture is very easy to understand, but you'll be surprised to know that till now nobody could find a formal proof for this conjecture. So it's very easy to understand, but no one could find any formal proof to give a kind of hints how to prove this. But using computers, people that could go as much as they can by using, so there is a limitation by computers. So, but people, they can go as much as they can, and they found that the result is correct, but not yet any formal proof of that. So there is another very cute example of this conjecture kind of thing. This is called twin prime conjecture. So we know that 2 and 3 are the only pair of primes which actually are consecutive, because you cannot have, except for 2, 3, any other pair of primes which are consecutive, because to have a consecutive primes, we should have at least one even and one odd. So the best that we can have a one gap. That means say 3, 5, there is a difference is 2, maybe 5, 7, the difference is 2, 11, 13, the difference is 2, and so on. So this kind of primes whose difference is 2 is called twin primes. And you'll be surprised to know that people, they have proved, I mean, Euler, Euclid have already proved that there exist infinitely many primes, but still people failed to prove there exist infinitely many twin primes. The computers, they could check it as much that they can, and they found that the result is true, but they failed to find that there exists any mathematical formal proof in number theory to have the formal proof that there exist infinitely many primes, twin primes. Okay. Again, there is a kind of anti-intuition. Number theory is quite peculiar. So it's the first one says that there exist infinitely many twin primes. Nobody yet could prove it, but the next result is very easy to prove. But it says that whatever big integer that you are giving to me, I can always find that many consecutive integers in which there will not be any prime. That means suppose you give me 100, I can always find a kind of 100 consecutive integers in which these 100 consecutive integers, none of them will be prime. For example, if give me any n, then I can always find this consecutive integer. So you can see that n plus 1 factorial plus 2, n plus 1 factorial plus 3, and so on. So there exist n such consecutive integers. And you can see that the first term is divisible by 2, second term is divisible by 3, the last term is divisible by n plus 1, and so on. So that way you can always have consecutive integers among which you cannot have any primes, whatever n, how big it is, then you can always find this kind of long gap where you cannot have any prime. Whereas the upper one says that there exists infinitely many primes. So it's a kind of anti-intuition, and that makes that topic more and more interesting. Okay, so again, the question that comes to our mind is there any application of number theory? So again and again, that actually haunted me with all the abstract things that we usually study. Are there any applications of such abstract things? So I'll just very briefly touch upon another very interesting topic, that is linear algebra in algebra. So when we talk about linear algebra, we usually, in our mind, the first thing that comes is a system of linear equation or some kind of matrices. So the question is, again, is there any application of linear algebra? So now I'm going to show you a few of the applications first. So usually we are very much fond about this animated movies, and you'll be surprised to know that in building these images, the linear transformation plays an important role. So many of us know about the MATLAB. So this is again like our Sage Math that just now I have shown you. So in case of MATLAB also, so the main, the full name for this MATLAB is Matrix Laboratory. So you can understand this, it actually works in terms of matrices and vectorial calculus and vectorial process. So we are always, sometimes we compress our data by using zip, or we make our songs or MP3 or MP4 players. So actually we are compressing our data. So there also linear algebra plays an important role. So now big data is a very buzzword. So many people are working with big data and all. So there also linear algebra, regression and all, they play an important role, how to analyze data, how to classify your data. So that's very important. So we sometimes get the signals for our mobiles, or sometimes from satellite images, we get our signals for, say, for ISRO or for NASA. They get all the very high resolution images from satellite images. Now the question is, when the signal, they actually come through the atmosphere using this ultraviolet ray or some noises, most of the times this data got corrupted. Now the question is, how did I, or how do we get the original image? And here the linear algebra, mostly the error correcting codes play an important role, and you'll be surprised to know that this linear codes are basically nothing but an element of a vector space over some field. So that means there are plenty of applications up there. But in my talk today, what I'm going to describe is about the number theory and abstract algebra, not about linear algebra. But linear algebra also has a lot of application in security, in cyber security. But the main topic for my today's talk is not about linear algebra, but mostly number theory and abstract algebra. We'll show that in our real life, this big number, and you'll be surprised to know that the whole big number is a prime number which has 904 digits. This kind of big numbers are actually protecting us from various places. For example, how did I get this? So if I show you this image of this big number, the first question it comes to your mind is it really a prime number? So the best thing that you can do, you can see the last digit. Since this is odd, you say that, okay, this is not even that I can say, but I'm surely not able to say whether this is prime or not. But believe me, that's a prime number, and this big prime numbers I can compute by using the small laptop. So again, if I use this kind of things, then I will, at the end, if I find some time, then I will go in details how this prime numbers we can find by using the small number. Okay, so here I missed this twin primes. So for example, if I give you this kind of interval, say 100 to 200, so it gives me all the list of all the twin primes. So you can see this, all the twin primes. If you say it's from 10 to 200, it gives you all the list of twin primes between the interval 10 to 200 and so on. Now I'm going to show you this, this small laptop is capable of finding big prime numbers. Okay, let me show you how. So for example, suppose I give you, so this is the big prime numbers that I am showing you. So it's the big prime numbers. See, this is the prime numbers. It's a huge prime number. Now, how did I, just one line code is sufficient because the code is already there. For example, suppose I put 2 to the power 10. So that gives me the next prime of 2 to the power 10. 2 to the power 10 is nothing but 1024. So the question is, this small code, next prime of 1024 gives me 1031, just fraction of second. So you may think that, okay, so this 10 is too small, why not 100? And if you put 100, so this is nothing but 2 to the power 100, the next prime of 2 to the power 100. So you can put it, this is 1000. So it will certainly take little more time, but I will show you how, say maybe 30 seconds, within 30 seconds, it gives you the actual answer. So this is the number, which is a prime number, which is just after 2 to the power 1000, and this slash actually stands for the next line. So you can join all of them, that will give you a number which actually contains around maybe 300, more than 300 digits of this prime. But here the prime that I have shown you, it's more than 1000. So this is the example that I have shown you, or not this one, maybe another one is there, but it took little bit more time, maybe 1.5 minutes to give me a prime of that size. Okay, so at the end, if I find some more time, then I will come into it to cover how to get this prime numbers. But first I will show how these prime numbers are important. Nowadays, we are very fond of using this cloud facilities like Google Email, YouTube, Google Calendars, and Google Meet, etc. So they're all cloud facilities that Google provides us. And sometimes we actually store our big data into the Google Drive. And you'll be surprised to know that to store them securely, these big prime numbers play an important role. Not only that, sometimes we buy online. So we order something online and we pay online, because sometimes while paying online, it gives us more discount and all. So while buying something or paying something online, so usually your mobile or your laptop browser, they actually connect with many places. So here three parties are important. One is customer, another one is the merchant, another one is the bank you are paying through online. So there are three parties, and how the communication takes place securely, that actually gives you a confidence, and the backbone for this is that kind of big prime numbers that actually gives us the confidence that okay, you can do it securely. Not only that, with the help of this WhatsApp, now this end-to-end encryption, this term is quite common or popular. Now many people, they actually talk about end-to-end encryption. In my talk, if I have time permits, I'll show on a bigger aspect how this end-to-end encryption works, and there also big primes are very important. Okay, so let me go very briefly why these numbers or how the numbers are important. Okay, so when usually we get into in the early morning, usually the first thing before going for brush, we actually go for our mobile and we put some of the symbols or some passwords or some of the notations on the screen so that the screen gets open. That means we put some password or pin to protect our data. When the day goes by and when we are in a very active mode, then also the mobile plays an important role, because at that time we usually go for chatting, or we do some online banking on in YouTube, we see something, or we surf for news, we buy many things, we play games, or we check our emails, WhatsApp status, and Facebook status, etc. So we do many of the things, and everywhere we need to put some password to protect our data. Not only that, even for our leisure time also, when we do some relaxation time, that then also we use mobile, and at the end, when we go for our bed, then also we stay with our mobile, and sometimes the mobile sleeps on our head. And all the things could be done by using lots of applications that are installed at our mobile. And with this lots of apps, the use of mobile is so easy that a child, and even nowadays these childs are doing much better than all of us. They are doing it very comfortably, and as a result we think that we are very confident and everything is within our mutti. So that's the thing. So before going into much details, let us just have a look at some statistics. It's little bit older statistics. It's a statistics from 2019. It says that Google processes over 5 exabyte of data per day. Now just have a look at 1 exabyte is how much GB. So 1 exabyte is 10 to the power 9 GB. So when we buy some computer or laptop, then we talk about TB. So this is 1000 GB maybe. Okay, but it's a 10 to the power 9 GB of data per day, and not only 10 to the power 9, 5 into 10 to the power 9 GB per day, and that also in 2019. Google handles 1.2 trillion searches every year. So 1 trillion is 10 to the power 12. Now you can think of in one day how much data Google deals with. Facebook is not also far behind. Facebook generates 4 petabyte of new data per day. 1 petabyte is 10 to the power 6 GB. Huge. 350 million photos are uploaded per day. User generates 4 million likes every minute. 4 millions means 40 lakhs likes every minute, and that too in 2019. WhatsApp has nearly 500 million users. It processes more than 70 million messages a second. 70 million messages means 7 crore messages a second. Now you can understand how big data that we are consumed every day. But with all this consumption, all this advancement of science and technology, at the same time, we also witness a lot of drawbacks. With the advancement of science and technology, we have already witnessed lots of looting, like ATM skimming. So many of the customers, they lost their money from ATM. Credit card frauds are also very common in today's scenario. So if you look at very recently, the credit card companies, they have introduced a new chip into your credit card. So at the back end, usually we had the magnetic tape. But very recently, you see that if you had only a magnetic tape, then your credit cards won't work. That means all the credit card companies, they have replaced their old version of the credit card with a new chip installed into the new credit card. So what is the reason? Do you think that that is only for decoration purpose? It looks good if you have a chip. No, it's certainly not. That is because many of the customers, they lost their money for this kind of threat issue made by some attackers. That's why the credit card has increased their security by introducing a chip into their credit card. This kind of emails are also very common. Suppose I get an email, say from ICICI Bank, and it says that we are actually upgrading the system. So please click here to provide your information. If you click here, it goes directly to this page. Again, an ICICI Bank link, and it says that put your user ID, password, and all. But if you look at very carefully at the address bar, you see that it is ICICIbank.C0M and not COM. That means certainly it is not coming from your ICICI bank. Not only that, it is not HTTPS. So it's only HTTP. Nowadays, it is recommended that if you are doing some online transaction, that means you are paying some money to some other unknown server or somewhere, always look at the address bar, and if it is only with HTTP, then it is recommended not to use any kind of transaction. If it is HTTPS, then somewhat you are safe, but it is not 100% guaranteed that you are safe. That means in digital world, nobody can give you 100% guarantee. So it is recommended that you should look at the sites where it has HTTPS and not HTTP. So this kind of attacks are known as phishing attacks, and many of the customers, they actually lost their many of their monies due to this phishing attack. Now this term hacking is also very common. So many of us, we play online gamings, and nowadays you might have heard that many of the online gamings are malwares. So hackers, they actually want to get into your mobile, and they want to get access about your personal data, like your mobile number, your bank account details, your password, etc. So there is a news. It says that it's a Israeli-based company. The name of that company is NSO, not the same as the US NSO. It's an Indian Express news. It says that this NSO group, they've made a malware known as Pegasus, and they used on many of the Indians around in 1999, 2019. They used it to get a lot of information about some of the activists and all. Not only that, it is assumed that we all know that death of Jamal Khashoggi. So he was an activist, and he was assassinated at Saudi Arabia. So his death was a kind of mystery. While the investigation came into picture, then it was found that his mobile was affected by this Pegasus malware. So what is that Pegasus malware? It's a very dangerous malware which can open your camera without having your knowledge. That means without your knowledge, it can open your camera, it can open your microphone, it can certainly look at your location and GPS location and all. So it's a dangerous software, and this is an Israel-based company who made this, and I'm sure there are many such other companies who has also made to use it to get more information about a particular targeted customer or targeted person. So you have to be very careful. Now you think about, if your camera is on without your knowledge, then what may happen? So you have to be little careful about all those things. So that's why Indian government is trying to ban many of the malwares which are suspected. So already Indian government has banned many of them, WeChat, Truecaller, and Beauty Plus shared it, many of them, and many are on the scrutiny level, which Indian government is going to shut down it very close. Within maybe within next year or next month or something. So okay. So there is in internet, there is another concept known as dark web or darknet. So usually that we are dealing with, our internet is a very small portion of the whole web system. So darknet or dark web is the major portion of internet portion. So what is the darknet? So broadly speaking, in the darknet, the users and the to whom you are sending your messages is protected. That means the identity of the senders or the receivers are protected. That means the anonymity is maintained. So now you can understand that it's very easy for the illegal drug dealer or weapon dealer or any illegal work that can be done very easily using dark web or darknet. So there are plenty of such techniques through which the illegal things can be done, and it's really difficult for the agencies to find the exact identity of the sender or the receivers. So the hackers, they usually sometimes hack some machine and they get all the information. Most of the time they use it for their own sake, but sometimes they sell it. You may find some news that in the dark web, some information is being sold for $8. So you may find that your user ID, password, or bank account details are being sold in the darknet at the cost of maybe $8 for 1,000 customers and all. So we have to be a little careful about all those things. So we heard about a lot of high-end cars like Lamborghini, BMW, Ferrari and all. So to increase the efficiency of the car, the companies, they have introduced a kind of small computer chip into a body of the car so that it can be like all the parts of the body, they can communicate with each other through that computer or small chip. A report says that that small computer can also be hacked, and if that can be hacked, then even if you have the driver in the car, the driver may be useless. That means from a remote place, the speed, the direction, the wind, everything that can be controlled from outside. So again, there is another news. It says that not only car, the pacemaker. So usually we use our pacemaker when we do have a problem at our heart at the some old age or something. When our heart does not pump properly, we need some external support, and we push or we put some or we implant some of the machine which is known as pacemaker, which actually controls the pace of your heart. It says that the pacemaker, high-end pacemaker, also have a small computer installed inside the pacemaker. That pacemaker can also be hacked, and now you can understand if that could be hacked, then what could be the situation for the patient. So in India also, we nowadays have kind of smart homes. So in smart homes, all the like smart kitchen, smart door, smart lights, smart TV and all. So where a smart thing like Alexa kind of thing that communicates with each other so that you can do operate things from outside. For example, you might have seen that Amitabh Bachchan ji is trying to operate his air conditioning machine from maybe from Switzerland. So that is known as IoT, Internet of Things, and that is considered to be a hot topic in today's research. Okay. So it says that if your home is smart, then also the signal which actually operates with, which actually communicates with all the smart devices can also be hacked. And if that is hacked, then all the control of your home may gone to some outsider, and who can actually operate your home from outside. So that's horrible. If we go a little beyond, then we have the cyber terrorism. So what is that cyber terrorism? So very recently, around 2017, it's only for 4 days, in May 12 to May 15, the whole world actually witnessed the strongest cyber attack on the world. It's known as WannaCry ransomware attack. What it says, suppose my machine is being hacked or is being infected by this WannaCry ransomware attack, then it says that, okay, don't worry, all the data of your laptop is intact. Just give me some money using this Bitcoin. So they have given some Bitcoin link. So again, why they have using Bitcoin? So it's like a darknet kind of idea. It's really difficult to find to whom you are paying the money. That means the anonymity is preserved here in using this Bitcoin technology. So it says that send, say, for me maybe $300 using this Bitcoin, then he will give me some key, and by using that key, I can get back the information. So that's the idea of one ransomware attack. But if somebody will tell me that, okay, give me this amount of money, then I will certainly say them that don't worry, I'm not going to pay you any money, because I'm just going to reinstall the whole thing and I have enough backup of my data. So I will get my all the data. But just think about the person or the main server. If the main server of some multinational company is being hacked or is being affected by this kind of WannaCry ransomware virus, then what they will do? Because they cannot reveal it publicly, because if they're going to reveal it publicly, then their share value will certainly go down. So secretly they actually paid within this 4 days. Many companies, hundreds of companies, they paid millions of dollars to the attackers to get back their data. And it was fortunate, we are fortunate that within that 4 days this has been resolved, and people were actually safe after that. But I'm sure in near future we are going to face even bigger this kind of ransomware attack. And this is the like a corona map. So it was the ransomware attack throughout the world where it actually affected. The red portion says that this part of the world were affected using this ransomware attack. So the question is, what to do then? So we have seen lots of attacks. A simple way could be we can stop using internet. So if we are going to stop using internet, then suddenly we are not connected and nobody can get into our mobile. We can use the old age Nokia big mobiles, then we are quite safe. But if I ask the question to mostly our younger generation that is it really possible for them to not to use internet, they will certainly answer it's not really possible for them to stop using internet. So we require some secure digital world, and here the term cryptography comes into play. So the question is, what is cryptography? So here, if you look at, I say that with less fear. So if you have some cryptographic backbone or support, then we say that it's less fear. I cannot say you are fearless. It's not commutative. So it's less fear. That means, again, I'm mentioning that in the world of digital world, nobody is 100% secure. So nobody can give you the guarantee that you are 100% secure, even if you have some antivirus installed at your machine. You'll be surprised to know that many of the antivirus companies, they produce viruses for the sake of their own production of antiviruses and all. So nobody can give you 100% guarantee that you are safe. But if you have cryptography as a backbone, then you may be a little bit safer. So the question is, what is cryptography? The term cryptography comes from two Greek words. Mind that they are Greek words, kryptos and graphia. Kryptos means hidden and graphia means writing. So cryptography is nothing but the art of writing secret message in such a way, if some guy, say A, wants to send some message to B, then if he wants to send the message to B, B can get the message, but some other guy, third person or bad guy, won't be able to get the message if he intercept the message in between. So that is the idea of cryptography. So to understand cryptography, we need to understand few terms. For example, suppose this boy wants to send some message to this girl through internet. But the problem is, there is one bad guy who is always trying to watch what is the message. That means he always tried to find what is the message is being sent from this boy to this girl. Up to this, there may be not that issue, but the problem is this bad guy has the ability to modify the message. That means when he will send some message, he has the ability that he can modify the message and can send the modified message to this girl. Then this girl may think that this message might have come from this boy, and so some confusion may arise, and that's dangerous. So the boy cannot sense the original message. So in cryptographic viewpoint, we call this original message as plain text, and he is going to send this plain text, not this plain text, to this girl due to this bad guy. So what he does, he will lock this plain text and get some other text which we call the locked message or the cipher text. So cipher text is nothing but the locked message. So he used some key to make a lock on that plain text to get cipher text. So he will send this locked message through this internet where the bad guy has some access. Now the process through which the plain text is converted into ciphertext using some mathematical tool is known as encryption. Now this lock message will receive by this girl. Now the girl should also have some key to open this message to get the plain text back. So the process through which the ciphertext is being converted into plain text is known as decryption. Okay. So encryption and decryptions are basically two parts of cryptography. So they are basically the constructive part. But like this bad guy, there may be other guys who are also trying to find the message or some loopholes or some drawbacks of the cryptographic scheme that these two guys are using. So this process is known as crypt analysis. That means they are analyzing the cryptographic scheme. These bad guys are known as adversaries. So adversaries, the main aim of the adversaries is to analyze the cryptographic scheme. So bigger concept is known as cryptology. So cryptology is a bigger subject which has two wings. One wing is the constructive one, which is known as cryptography. Another wing is known as crypt analysis. So cryptology is nothing but the combination of constructive as well as the destructive part. And to understand cryptography, two things are very important. One is symmetric key, another one is asymmetric key. See, here we require two keys. So if these two keys are happen to be the same, we call it symmetric key or private key crypto system. But if these two keys are different, then we call it asymmetric key or public key crypto system. Okay. So there are famous AES or RC4, though nowadays this RC4s are no more because we found a lot of loopholes for this RC4. So people are nowadays afraid of using this RC4, but AES are still useful. So they are examples of symmetric key crypto system, whereas RSA or Ilgamal key crypto system, they are examples of public key or asymmetric key crypto system. Okay. So let me give you some examples. So again, this is an historical example. It was done by Julius Caesar, and if you look at, he was there around 50th BC, so more than 2050 years back. So let us try to explain the whole scheme by Julius Caesar using some English alphabet. Suppose Julius Caesar wants to send some message to one of his subordinates, say one of his commander, and assume that commander is, say, fighting at some war front which is far away from, say, Rome, and Julius Caesar is in Rome. So Julius Caesar wants to send some message to his commander by using some, say, message carrier. Now, if he sends some original message or the plain text, then if the message carrier is being caught by the opponent or the enemies, then the message will be read by them, and so the plan may be destroyed. So what Julius Caesar did, he did a scheme which is known as Caesarian cipher or SIP cipher. Okay, so before going to war front, Julius Caesar and his subordinate, they decided that they are going to use some k value equal to 11. So I am going to explain what is that meaning. So before going to war front, remember Julius Caesar and his subordinate, they decided that they are going to use the value k equal to 11 for future purposes of their transmission. Suppose after that Julius Caesar was in Rome and his subordinate was in some war front which is far away from Rome. Suppose Julius Caesar wanted to send this message, cryptography is fun, through some messenger. Now what he does? He did actually what he did. So he first, we assume that all the alphabets are in capital and he uses only capital alphabets. That means there are 26 alphabets. So Julius Caesar just renamed them. So kind of roll number. So roll number of A is 0, roll number of B is 1. So roll number of Z is 25. So what Julius Caesar did, so here the plain text is C. So if you look at the value of C is 2. What Julius Caesar did is he just shift 11 times to the right. So that means 2 plus 11, that becomes 13. So C will be replaced by 13. Now have a look at R. So the roll number for R is 17. So if you shift it 11 times, that becomes 28. But it's 25 is the last. That means here it comes here somewhere. What now to do is just cyclically shift the whole thing. That means 28 divided by 26 and take the remainder. And the remainder is Nothing but 2. 28 divided by 26, take the remainder is 2. So R is shifted by, replaced by C, and so on. Now when the commander will get this message, and as he know that the Julius Caesar made this and he used k equal to 11, what he did, he just left shift everything 11 times to the left cyclically, and he will get back the original message. Now if I ask you the question, how to explain the whole thing by using group theory. So while we study group theory, or while we teach group theory, so there may be some good examples to motivate the students. So it could be a very nice example. Now, if I ask you the question, can you explain it by using some group theoretic technique? So let me give you an example of a group which is very common to all of us. So from our very childhood, we are quite familiar with this kind of watch. So usually the watch is from 1 to 12. And usually we never say that the time is 13 hours unless we are in military or in rail or somewhere in airport. So after 12, it becomes again 1, and so on. So now the question is, can we explain the whole thing using this kind of group? Which group is associated with this watch? This is nothing but addition modulo 12. So Z12 plus is the group. So here also we can explain very easily by using Z26. Now we have some mathematical function, encryption function, which takes some plain text x, and how it works? It works actually x plus k. Here k is nothing but my key. In that previous example, the value of k was 11. So x plus 11 modulo 26. So in general, you can vary k. So that value has to be known to your subordinate as well as Julius Caesar. And the decryption is done by y minus k modulo 26. So while making them understand the cyclic group, Zn and all, if we can explain this kind of example, they may find it more interesting and all. Okay. So now the question is, so in Julius Caesar's case, you found that in case of Julius Caesar, both the receiver and the sender, they should use the same key. That's why the idea of that scheme was symmetric key cryptography. Now assume that this boy wants to send some message to this girl through internet where a bad guy is trying to find the message. So, and also assume that this boy and this girl, they stay far apart, say opposite half of the world. So for them, it's really not possible to beforehand to have the common key. So in case of Julius Caesar, both of them, Julius Caesar and his subordinate, had the same key. But since they are staying far apart, it's really not possible to have a common key. So the question is, what to do under this situation? How to have the common key? Now you may think that, okay, send first some Google by Gmail or WhatsApp that we are going to use this. But how can you believe Google or WhatsApp that they are not going to get your information? So they may know, and they cannot come closer because they are staying far apart. Now the question is how to have the common key. And it was a long-standing problem for many years. And for the first time in 1977, Diffie and Hellman, they for the first time came into picture. But before going to, and that is considered to be the changing phase, and then actually the public key crypto system came into picture. But before going to the public key crypto system, let me explain naively from our day-to-day life example. Okay. Suppose, so here we are, many of us, we are all faculty members, so we all are aware about our examination system. Suppose there is some university and they have some controller of examination. So sometimes we rely upon some external expert. That means a faculty member which is not from that university. So he's from some other university. So usually that guy, usually the external expert, that guy little far off from the university or something. So what the external expert, the controller of examination, he wants that this external examiner should prepare a question paper and he should hand it over to this controller of examination securely. Now this controller of examination, he is fond of having some security protocol and all. So he is very fond of having some security. So for that, what he does, he prepares some box, lock and key. And suppose some university stamps are on that. and he sends using this postman this box and key to the examiner. So now examiner he will receive this box, post and key, lock and key. So when his question paper is done, he puts it into the box and then he has his lock and key. So he will lock it. Now he's going to send this locked box to the controller of examination through this postman. Now my question is, what could be a very simple protocol so that this box could be reached to the controller of examination safely? If I could have some one-to-one correspondence with you in a classroom or something somewhere, then it would be easier for you to give me the answer. I'm sure you will be able to do that, but certainly it's not really possible here on the digital platform because we have some sparsity of time. So I will just give you some answer, but that is very interesting protocol that I'm going to show you. Suddenly, this paper setter will not give the locked box and the key to the postman to send it to this controller of examination, because midway he can open and get the question paper. So what he can do, he can send this box to the controller of examination without sending this lock and key, without sending this key. Now for the security reason, the controller did not have any extra copy of that key. He might have some extra copy, but since he is very cautious about security, he didn't make any extra copy of this key. So if it comes here, he himself won't be able to open this. So you may say that, okay, when he gets this, you may send this lock, this key again through this postman, and he will get this lock and key and he will do this. So this idea is known as secret sharing, again a kind of very important primitive of cryptography. For example, few years back when you get your credit card, you find that the credit card or debit card, they come first and then the pin comes into another through some postman in some another envelope. So it's a kind of sharing your data. So that's again, when you buy something, you sometimes put your all the credit card details, then some OTP comes to your registered mobile, and then you have to again put the OTP into the proper place, and then only you can buy something. So that's a kind of sharing your data to authenticate you and all. So that's known as secret sharing. But in today's talk, I'm not going to deal with secret sharing. I'm going to give another very innovative idea how to share this kind of data. Okay. So what he does, he will give it to him and he will send it to controller of examination. Now the controller of examination does not have the lock and key. So what he does, he will put another lock and key into the box and he will send it to the external examiner. Now the external examiner has his own key, so he can open this and he can send it to the controller of examination. Now the controller of examination has his own key. By using his key, he can open this and he can get the question paper. So it's basically why I am giving this kind of a little bit complex to you. Maybe you may think that, okay, this looks quite innovative, but the previous secret sharing scheme could be better option. But why I am telling it, it would be quite clear when I will go to the digital version of this. Okay, but in digital world, we cannot underestimate anybody. So again, I am going to show you, because cryptography is not about just the construction part. So as I mentioned, some attackers are always there who is trying to get some kind of loopholes into your method. So again, I am going to give you another attack. Suppose the same scenario, but the postman is little bit problematic. So he is a kind of attacker and he is fond of doing mathematics, and he wants to solve the question paper before giving it to controller of examination to check whether this is a standard question or not, etc. Okay, so what he does, when he has a box, lock and key, what he does, he will provide a similar looking lock and key on his own. So this part is his own lock and key, which looks almost similar to that, not exactly the same as the given by the controller. What he does, he just gives this box along with his own lock and key. Now the question setter will make the question paper and put it into the box and lock it and gives it to back to the postman. Now what the postman will do? Postman will put the actual lock given by the controller of examination and gives it to him and again gives it to him. Now the external examiner will think that, oh, that's nice. It's from the controller of examination. So he opens his own lock and key and sends it back to controller of examination. But in between, what he will do? He has the lock. He has the lock and key with him. What he will do? He can open this. He can modify the question. He can take a photocopy of the question. He can sell the question, whatever he can do. And after doing that, he can put the lock on his own and gives it to the controller of examination. Now what controller of examination will understand? Okay, it comes from the external paper setter because it has the stamp from university of some university of his university. What he will do? He will again put a lock and key here and he will again give it to him. What he does? He just opens it and again sends it back to the controller of examination. Now the controller of examination is very happy because he his own lock and key. So he can open this and whatever question paper he gets is nothing but a modified one or maybe the leaked one. So that's the nice attack on the digital world. So that's basically the crypt analysis of the whole scheme. So that's important. So to understand cryptography, we also have to look at the weaknesses. So it's a game, parallel game is always going on between cryptography and cryptanalysis. Somebody have some scheme and then somebody finds some weakness. Again, somebody overcome that problem and somebody again finds some problem and so on. So that's a game. It's an interesting game. Okay. So while doing this, in our real world, we should have some extra features that now we should take care of. Firstly, the question paper really comes from the external paper setter. That means the external or the controller of examination should have the confidence that really the question paper comes from the controller of this external paper setter. No one else read the question paper during transit. No one else modified the question paper during transit. Later on, if suppose after the exam, say some dispute on the question paper came into picture, then it should be the responsibility for the question setter. That means the paper setter, external paper setter should not or cannot deny that he has made this question paper. That means all these mechanisms that we should take into account while constructing this kind of schemes. Now I am coming to the digital version of the whole scheme. Okay. So as I mentioned, this is the situation where the sender and the receivers are there, but unfortunately they stay far apart. So Diffie and Hellman, for the first time, they came into picture to have a scheme which is known as Diffie-Hellman key exchange protocol. So I'm not going to details of that, but I'm going to explain another number theoretic concept which is given by Shamir, Adi Shamir. So this scheme is known as RSA public key crypto system. But before going into much details, first let me try to understand what is public key crypto system. Now, if I ask you the question, if someone wants to send some message from this boy to this guy, who should take the initiative first? It should be the boy should initiate first or the girl should take the initiative first? Your very quick answer would be the boy should take the initiative first because he is going to send the message. But if you think more carefully, then it should be the girl first, because if the boy wants to send some message to the through say WhatsApp or something to this girl to her mobile, then the girl should have at least some mobile with a valid connection. Unless the girl should have some valid number, valid connection with some balance or something, this boy won't be able to send the message. That means the girl should take the initiative first to have the infrastructure. That means infrastructure should be made by this girl first. Then only the boy would be able to send the message. Now, when the girl made this infrastructure, so she is going to give the information to this girl, a boy. I mean, it should be the boy's responsibility to get the information. For example, in case of public key crypto system, while doing that, the girl should have two keys. Instead of having one common key, the girl should have two keys. For example, when I have prepare my email ID, when I make my email ID, the email ID has two components. First component is the email ID name, that means username, and the second component is the password. So email ID is actually made public. I can put my email ID in my website or somewhere else, in my WhatsApp status or everywhere, but I keep with me the password with me. I do not share my password with anybody else. So when somebody wants to send me some email, it's his responsibility to collect my email ID. So he has his email ID, my email ID, then using that email ID, he sends me some message. When I get that message, since I know the password of that email ID, only me can get into that email to get the email ID. So that's the idea of public key crypto system. Like when the boy wants to send some message to this girl, it's the responsibility for the girl to have the infrastructure. That means she is going to make two different keys. One is public key, another one is private key. She makes the public key public, so anybody can access this public key, but she keeps the private key with her secretly. That means only she can understand or know the private key. Now when the boy wants to send some message, he first collects the public key. So this is available to anybody since a public entity. So he can also access this public key, and based on that public key, he sends the message. Now, since this girl has the private key with her, only she can decrypt this message and nobody else. So in between, if he gets this, he won't be able to get the information. So that's the idea of public key crypto system. Okay. So before going into that, how much time? Yeah. So before going into that, let me explain exactly how it's happening. So RSA, for the first time, they came up with a scheme, and you'll be surprised to know that that scheme is basically based on a mathematical problem known as factorial problem. Factorization problem, not factorial, factorization problem. It's really difficult for a mathematician to believe that factorization is a difficult problem. So what is the difficult problem? If I give you 35 and if I ask you, can you factor 35 into two prime factors? You can certainly say that, okay, I can always factor 5 into 7. If I give you n equal to this, and if I ask you, can you factor this? You, after some time, it may take some time, but you suddenly get the factors are 101 and 103. If I give you this, you say that, okay, I'm not going to do it by hand. I can write a small programming and that will give me this answer. But if I give you this, it's a very big number. And if I ask you, can you factor this? And you will be stuck. And you will be very happy to know that not only you, but a supercomputer will also start, because this is nothing but the product of these two big primes. So each of the primes, they have around 300 digit within this P and Q. So n is, this value n is nothing but the product of this P and Q. As I mentioned earlier, how did I get this two big primes? So that's a separate issue of number theory. But if you assume that they are prime numbers, then for computer, finding that primes are easy. I can assure you this prime, you can get it very easily. I have already shown you how to get this kind of primes by using my small laptop. I haven't shown you the code, but I have given you the evidence that, okay, they are capable of, my small mobile, my small laptop is capable of producing this big prime numbers. And for computers, making the product is also easy. That means if you have P and Q, then you can easily find or calculate the value of n. But unfortunately, even for supercomputers, if I give you the value of n, then for supercomputers also, it's not possible to give you the value P and Q very easily. Say for supercomputers, it may take more than 1,000 years to give you back these values of P and Q. So that may not be of that good interest that after 1,000 years you get the message. So that is not really possible. That's why people use till now this kind of concept. So that is called factorization problem, and you will be surprised to know that there is not yet any efficient algorithm. That means any algorithm which can be done by using your computer. Computer means the normal hardware that we use even for supercomputers. Mind that quantum algorithms are available, Schnorr's algorithm are available to have a factorization of that big number. That is quite efficient. But the problem is the algorithm is available, but the machine is not available. So the machine, the quantum machine that can deal with this big number is not available. Like in Raman, the Raman is ready, but the RAM is not yet present. That's why but we cannot think of breaking this kind of numbers using quantum machines or quantum computers. But if one day the quantum computer will arrive, I'm sure that it will certainly arrive in some day. During that time, it will not be possible to use this kind of schemes. Okay, but for till now, these schemes are capable of securing our data very easily. Okay, so the problem, the basic problem or the basic motivation or the basic backbone for RSA crypto system is that if I give you two big prime numbers and if I make a product of it, you can always very easily find the value of n. But if I only give you n, then it's really difficult for machines, even for supercomputers, to give back this p and q. So that is why this is known as computationally hard problems, and they are called believed to be hard problem because not yet any algorithm is known publicly which can factor these big numbers very efficiently. Okay, so now let us try to explain how this works. Okay, so it's a public key crypto system. As I mentioned earlier, to have this kind of public key crypto system, the sender and the receiver, it should be the receivers or recipients activity should come first. So the recipient should make the infrastructure. So here also the recipient will have the infrastructure first. How she will going to do? She will going to choose two big prime numbers p and q. Okay, now as I mentioned, it's really very easy to get p and q of that size. Then she is going to compute phi n. So what is that phi? Phi n is nothing but the Euler phi function. So we know that Euler, what is Euler phi function? So Euler phi function is nothing but we denote it by phi n. So phi n is nothing but number of positive integers less than equal to n and relatively prime to n. Relatively prime to n. To n. So what does it mean? So if I consider phi of 6, I consider all the, so this is the number, that means cardinality of some set. We can see that 1 and 5 are the two elements which are less than equal to 6 and relatively prime. That means the GCD of 6 and 1 is 1, GCD of 5 and 6 is 1. So this is nothing but 2. So if I consider phi of 7, we see that this is nothing but the cardinality of this set 1 2 dot dot 6. All the elements which are less than 7 from 1 to 6, all of them are relatively prime to 6. That means phi of 6 7 is 6. So in general we can understand that if p is prime, then phi of p is nothing but p minus 1. We also know that phi is a multiplicative function. That means if m and n are two relatively prime integers, then phi m and phi n can be written in this form. And this can be proved very easily by group theoretic techniques by using the concept of cyclic group Z in M and Zm cross Zn. And since they are cyclic, so since GCD of m and n are 1, that means they are relatively prime, these two groups are isomorphic. So the number of generators of this group is this, and number of generators of this group, only this group is this, and number of generators of this group is this. And since if A is a generator of this, then there always exists by Chinese remainder theorem x and y, which is a generator of this. So by using that, you can always find the value this. So the proof is very simple by using group theoretic technique. But if you do this by using classical number theory, the proof is little bit lengthy. But that is also not very difficult. You can see it in any number theoretic book. Okay. So by using this kind of concept, so another thing we must mention that if we have the value like n equal to p1 alpha 1, the as Euclid mentioned, pk alpha k, if I know the prime factorization of n, then the value, finding the value of n is very easy. Then we know that this is nothing but the multiplicative function, and you can distribute phi over each of these pi's, and you have this kind of formula that you all know, that phi n. But the problem is, like factorization, if you don't know the prime factorization of n, then this value, finding this value is again difficult. That means not yet any good algorithm are available which can compute the value of phi n without knowing the prime factorization of n. If the value of n is very high, like 900 digit or 1000 digit, then you can understand to check which of the elements are relatively prime or not, then it would be huge. I mean, it would be a 1000-digit long integer, and you have to check for each of them. It's for a supercomputer, it may take 1000 years to do that, because there exists till now no known algorithm which can solve this problem. That means given phi n, find the value of, so given n, without knowing his prime factorization, find phi n. So that's also a difficult problem. So based on that, RSA crypto system is valid. Okay, so what again I am repeating. So the girl will first choose two big primes p and q. They must be different, but they must be of the same size. Then since she knows p and q, she can very easily compute phi n, because phi n is nothing but she will first calculate p minus 1 and q minus 1. As I have already mentioned, if they are relatively prime, then you can make it this property, and each of these phi of p is p minus 1, phi of q is q minus 1. So what she will do, she will just find p minus 1 and q minus 1 and make the product, whatever will be the value, that will nothing but the phi n. Now she is going to choose an integer e which is relatively prime to phi n. Again, you will be surprised to know that the Euclid algorithm is very efficient to find the GCD even for bigger numbers. So by using Euclid algorithm, she can very easily compute the value e, which is relatively prime to n. Now she is going to compute the multiplicative inverse of e. Since e and phi n are relatively prime, there exists a multiplicative inverse of dE. So by using extended Euclid algorithm, you can again construct this value of d very easily. So there are very easy algorithm which can give you the multiplicative inverse of d in phi n. So now she has calculated many things like n, she has calculated also phi n, she has also calculated e and d. So among this, she is going to make public this value n and e. That means this value could be known to anybody, and she with her keeps this value p, q and d. So mostly d. So p, q will not be used by this girl, but d will be used in future for decryption. So e will be used for encryption. Now these values n and e are public, and this d value is kept secret with her. Now what will happen, this boy wants to send the message. So before sending the message, this girl has already prepared the infrastructure. Now when he wants to send the message to this girl, first he finds the public value. So here the public value of this girl is n and e. So she collects this public value from somewhere. Now he wants to send the message m. What he is going to do, he will just compute m to the power e modulo n. See, m is the message, and e, he has already received it from somewhere as a public value. So m to the power e modulo n, and you will be surprised to know that for these bigger numbers, this square and multiply methods are very efficient to get even for bigger numbers. So he can compute very easily this value c. So c is the ciphertext. Now he sends this value c to this girl, and you will be surprised to know that she has this value d. So she will just calculate c to the power d modulo n, and that is nothing but m. A very simple group theoretic technique is used here, just Fermat's little theorem and the Euler's theorem, to get that c to the power d is m. That means C gets this message. Now what's happened for this bad guy? So what he knows the value of C, he knows the value of the public entity like N and E. So they are all public. So N, E, and C he knows. Now the problem is he knows E, but he needs to calculate D to get, because D is secret to her. Now the problem is to find D from E, he needs to find the value of phi n, because D is nothing but the multiplicative inverse of E in phi n. But the problem is this guy has no clue about the P and Q, because he has the value n, but as I mentioned, having the value n, finding P and Q is a difficult problem, not only for him but for supercomputer itself. That's why he will not be able to find the value of phi n. As a result, what he will happen? As a result, he will get the value of, cannot be able to find the value of phi n, and as a result, he won't be able to find the value of D. So he won't be able to get the information. So based on that, it's a naive way of saying, but it has a different way to prove it. But okay, so it's a security issues are there. So I'm not going details about all those things, but you can see that simple group theoretic techniques are useful to get the information. Okay, so till now, this RSA crypto system are very much used while we buy something online, or even in WhatsApp, they use RSA crypto system, but in a different form, in elliptic curve crypto system. Those who are interested with algebraic geometry, they are very acquainted with elliptic curves, and you'll be surprised to know that in cryptography, elliptic curves play an important role over some finite field. Okay. So till now, this RSA crypto system is very popular and very secure itself, since factorization is considered to be a hard problem. Now I am again giving you another attack on RSA crypto system, which is not a attack directly on the crypto system, but how you are going to use it. For example, suppose somebody wants to sell Mona Lisa. Say French government, they want to sell Mona Lisa, and they want a kind of auction. Okay, so many people will participate in the auction, and they are going to bid it. So the idea is whoever will be the highest bidder, for example here 33, so you can understand how good is this 33. So it should be 33 maybe million euros and all. So he will the Mona Lisa will be given to him or her, who is the highest bidder. So suppose the French company or the French government, they want that during this lockdown period, it's really not possible to have a kind of physical auction. So what they did that, okay, they are going to do it in online mode. And for that, they require a very robust, very strong crypto system, as well as they want that the whole process should be very transparent. So the question is how to do that. Okay, so what they decided, French government, suppose they want to use this RSA crypto system, and so that's why they prepared the public values like N and E, and they keep secret with them the value of P, Q, and D. So each of the bidders, they will have their own bid value, that would be the plain text. They will multiply it by 100, and then that will be their plain text, and then they are going to encrypt the value. For example, suppose this guy wants to buy this value, this Mona Lisa, he sends 100, so it is 100 million in euro. So I just have a simple conversion rate. So I made it. So the plain text is, instead of 100, I will always multiply it by 100, and that $1,000,000. So what is his plain text? His plain text is basically 10,000, say $10,000 million. So what he is going to put, he is going to encrypt 10,000 by using this public value. So he encrypts this 10,000 value by using this public key. That means 10,000 to the power e modulo n gives you this value. Okay, and this this French government, they put it publicly, like he has given this value, so nobody can deny later on that any malpractice has been made. But as soon as this guy gives this value, a guy, he also puts this value. Now the question is how he makes this value. I will come into later on, but assume that just looking at his value, he puts this value. Now say another guy, another girl, say she wants this to be 999, and as I mentioned, I multiplied it by 100 to make it in Indian rupee. So that 99900 million Indian rupee. So she has given the price. So she made it like this. So her ciphertext is this. As long as she puts her ciphertext here, the guy came and he also put something here. Now, say after a certain date, the government, they displays the overall who is the winner. So all the plain text, they made public this value. This is the value of D. So now anybody can calculate and check whether these values are correct or not. So as I mentioned, this was 10,000. So 100 into 10. So it was 10,000. And this boy's value was 10,000 plus 100. Okay. So suddenly this is bigger than this one. Now look at here. This girl gave 99900 and this value is 100899. Okay. So who is the winner? This boy is the certainly the winner because this is the maximum value. So this Mona Lisa image or picture would be sold to this boy. Now the question is, after just looking at each of the ciphertext, he has given C2 and C4. Now how he calculated this value? If you look it carefully, 10,000 and this is 10,100. This is just 1% of this value. So M2 is nothing but the 1% increase of this value. Similarly, if you look at 1% of this, this is nothing but 999. And if I add 999 plus 99900, I will get this. That means the boy has always given 1% increase of the submitted plain ciphertext. So the question is how the boy made this just looking at the ciphertext. So what he knows the values of E and N as well as he knows the values of each of the ciphertext. Now I am going to show you how this attack can be made. Okay. And that is due to the homomorphic property of encryption scheme. So if you look at what was the encryption function here, the encryption function was, if you have, so the values of N and E were the public and D was the secret. So they are public, it is known to all. It was encryption function was M to the power E modulo. So I can put it capital E encryption. Otherwise E and E may get confused. And this. And how the decryption was made? Decryption function was done by this. So it was a ciphertext, say it was a ciphertext, and this is C to the power D modulo N. Now just have a look at what I want to do. Suppose I want to have 1% increase of the plain text value. Now if you look at why I have multiplied all the things with 100, now it will be clear to you. Now if I want to make 1% increase of this, then what I will do, I will multiply it by this. Then whatever will be the value, that will be 1% increase of the value of M, right? Now I will use this idea. So C1, the first participants was 10,000 to the power E modulo N. Okay. Now what the guy will do, the guy will calculate first this. Now remember, we are all doing this in modulo N. This is the product of two big primes, P and Q. Now this inverse I want to find in N. Since this is the product of two primes, like you have some multiples of this, like 2 and 5 are the 2 and 5. So 2 square into 5 square. And this 2 and 5, they are relatively prime with both P and Q, because P and Qs are very big primes. So this 100 is relatively prime with N. So you can always find the multiplicative inverse of 100 in N. Okay. So what the bad guy will do? So he is going to construct C2. So he knows C1. So he knows C1. He just going to multiply with this value 101 to the power E. And as I mentioned, 100 inverse is also there, E modulo N. See, this value is known to the attacker because in the website, the first guy have already given this cipher text of this. He is going to increase by 1%. So he knows 101. He knows the public value E. He wants to have the inverse of this, and he knows the E. He knows the value of N. So everything he knows. Now what is C1? C1 is nothing but 10,000 to the power E. And all the exponents, they are in E, and we are dealing all the things in Zn star or maybe Zn with respect to dot. So we are doing it in the ring Zn plus dot, and that is with respect to multiplication, that is commutative. So you can very easily put inside this 101 into 101 inverse whole to the power E. So if I decrypt this, if I put a D on that, I will get this value, which is nothing but the 1% increase of that. That means he can do, without knowing the cipher text, he can always, without knowing the plain text, he can always manipulate the cipher text in such a way that he will always gain. So that's why this is known as the bidding attack. And so the idea is you cannot use bidding you cannot use the bidding or the auction by using RSA crypto system, because it's a homomorphic property. Why this is homomorphic property? Because you can see that encryption of M1, M2, encryption of M1, M2 is nothing but encryption of M1 into encryption of M2. What is we used it here? That's why. So all of them, they are encryptions. So we can multiply them and we can put it inside, and as a result, after decryption, whatever we'll get the 101% increase of this value. That's why he is always winning. And in real life also, when for the first time this auction was held with respect to this RSA crypto system, this practical attack actually happened, and the company actually who wanted to buy in a through this malicious way, they actually own the bidding in all the time. So that is an idea that we should always keep, that you have to be careful about whatever secure things that you are going to use. So now the question is, how did I get all this prime? So I don't have much time now to explain all of them, so I'm just skipping them. But again, this is an interesting idea how to get this bigger primes very easily. So they are basically based on some probabilistic algorithm. To prove this, we need to have very simple group theoretic technique and a technique called quadratic reciprocity, Jacobi symbol, Legendus symbol, and all. Based on that, this is a very small algorithm that you can see, and based on that, I already told you how to get the bigger primes and so on. So if you want to learn more about it, you can just look at the chapter 12 of my book. So there I have mentioned it in a algebraic way how to get this big primes very easily. So this is maybe one of such big primes that we can easily, even my small laptop can find it this big prime maybe in 1 minute or so. Okay. So now the question is, with this big prime, how exactly we communicate with each other? So very quickly, I just briefly explain what is the bigger idea of this end-to-end encryption. So suppose this sender wants to send some message to this girl. So as I mentioned, like public key crypto system, it's the girl's responsibility. So suppose this girl wants to have the message using say WhatsApp. Now what is done? The girl should install the WhatsApp into her mobile. So while WhatsApp is being installed at her mobile, two things happened. One is public key, another one is private key. So when we install WhatsApp at our mobile, two keys are generated. One is public key, that is made public, another one is secret key. So this public key is sent to the server of WhatsApp. So whenever this public key is generated online, we send first. We actually don't know what is happening, but the mechanism is such that whenever you install this WhatsApp at your machine, the public key automatically is sent to the server, and at your machine this private key is kept. That means only this guy knows the private key. Now when the boy wants to send the message to this girl, first the boy requests the server to send the public key of that girl. Since the server has the public key of that girl, see, the server sends the public key to that boy. With that public key, he encrypts his message. So it's a locked message. Then this locked message comes through the server of WhatsApp, and it comes through the girl. Now, since the girl and only the girl has this private key, the girl can only decrypt this message. See here, WhatsApp claims that not even the any third party, it's not also possible for WhatsApp to decode this message, because the WhatsApp has only the public key but not the private key. So that is why it is called end-to-end encryption, because encryption and decryption are being done at two ends, and WhatsApp even won't be able to get the message according to WhatsApp. So while doing this digitally, as in the case of the external examiner and the controller of examiner, we had the idea digitally, we also have to have similar kind of idea. Like no one else has read the message in transit. That means these two guys should have the confidence that no one else has read the message in transit, no one else has modified the message in transit. The message really comes from the sender. So the girl should be confident enough that the message has really come from this boy, and later on the boy should not be able to deny that he has sent the message to this girl. So all these ideas has to be embedded within our system, and to embed this we need few technical terms which are known as confidentiality, integrity, authenticity, and non-repudiations. And to achieve this, cryptographic primitives are used. For example, symmetric, asymmetric crypto system like RSA crypto system, hash functions, MAC, and signature. Each of these topics are a building block of cryptography, and they are basically different books can be written on each of these topics. So they cannot be covered in a small amount of time, but one can talk around 5 hours on each of these topics. So within that help, the WhatsApp, they have a kind of, they use Signal protocol to implement this end-to-end encryption. And if somebody is interested, they may go the white page by WhatsApp, and there they have written how the Signal protocol actually works in details. So that's the end of my talk, and I want to acknowledge Google for providing me all the information and necessary images. So I'm thankful to my funding agencies like Department of Information Technology, Government of India, DRDO, YZ. They are both Ministry of Defense under DST Serve, DST Matrices, NBHM, and two Japanese organizations, JSPS and JST. They are from Government of Japan for providing me financial support for all my research and my team members. And all the materials that I have covered, many of them are mathematically explained in this basic modern algebra. It's a Springer book. So if any question, so sometimes it's not always possible to attend all the questions, but I am here as long as the organizers are allowing me to answer all your queries. But if you miss something, or if I miss something, please do not hesitate to send me email to my email ID. And thank you. So that's the end of my talk. So anything?
Giving such an informative and interactive presentation. He very elaborately and explained mathematical aspects of cryptography. history of development of group theory and number theory, and then gradually explaining its application in. It was indeed an wonderful learning session through lots of interesting example and case study, and it actually now storytelling. So thank you very much, sir, for such an amazing lecture. Now I shall request on to take questions that question answer box. Anisha, please.
Thank you, madam. But there are few questions. Okay, so let's start. Uh, excuse me. Which software tool is used by data analyst professional?
Mostly they use Python. So there are one very ID, so good thing. Jupyter is there, so you can use Jupyter to use this. So mostly the Python they use as software. I mean, as a background, as a programming language, and Jupyter is a good software where you can. It looks like Sage itself, so you can use Jupyter there. There are many others. PyCharm is there for Windows, but Jupyter is mostly used. So I love Jupyter. Yeah.
Next, the calculation of modulo is done in decimal or binary numbers.
So if you look at the mathematically, then basically you do it in modulo something n. But the idea here is we use square and multiply method. So that I haven't explained. So in case of say you want to calculate x to the per n, for example, say if you want to calculate say x to the per n, sorry, x to the per something x to the per e modulo n. So what we do, we first make it binary, and based on that we use the term square and multiply. Sometimes we only square and sometimes we square and then multiply. So when the machine works, it certainly works in binary, because machine, we know that machine only understands in binary. But nowadays some processors are being made which actually do some specific problems or specific architecture they follow. As a result, they can be made over some 2 to the per f 2 to the per n field. So instead of only binary, so having this kind of architectures nowadays, people are trying to make for a particular. So that's not a general purpose machine, but to do some specific computation more faster or more efficient, they make it like this. So machine, when the machine works, it makes it in a binary, but mathematically it on modulo n. But before that, we made it binary. The value of e is made in binary, and based on the position where it is 1, depending on that, we either square and multiply with a certain value. That is an efficient way of doing modulo n by using square and multiply algorithm.
Okay. Next good problem. Next question. What is the role of CAPTCHA in cybersecurity?
Okay, so it's a basically you can think in that way. So why in CAPTCHA what usually we put? So in CAPTCHA usually we put some distorted characters like A written in a different way, some numbers written in a scrambled way and all. So basic idea is that, so by using nowadays you all know or heard about the term artificial intelligence. So some programmings are being made which can try with all possible choices, right? Suppose I have my password, say 5, only alphabets are there. Suppose it's only capital alphabets. Then the machine has to guess only 26 to the per 5 many options, right? Now, if you don't put CAPTCHA on it, machine will automatically do all the exhaustive searches. And the CAPTCHA means the machine has to put, or the attacker has to put at every level some distorted image. That means it has to guess what is the distorted image or what is the distorted character. As a result, it is really difficult for a machine. So our brain or our human brain is very powerful. We can recognize it very quickly, but the point is how the machines can recognize that distorted characters. That's why people are putting captcha, but the bad news is now there are AI algorithms which are capable of even guessing the captcha characters. That means within maybe 1 year, there may captcha may come in a different way. That means people are already capturing captcha. So that could be a dangerous situation for us. That's why captcha is being used to give you extra protection that machine should not give you the answer or cannot provide the information very quickly. Exhaustive search could be stopped. And but again, the machine is capturing captcha. So hope that is understood.
Okay. Our next question. Cryptographic application in blockchain, and one of blockchain application is Bitcoin. How safe, secure, reliable, risk-free it is and its future?
Okay, so this blockchains are now very hot topic because it's a broadly speaking, it's a like big ledger. So anybody can can keep the account for others. So any modification or somebody did something wrong, so others will be able to capture it very quickly. The problem is here, the day by day the size of this laser is gradually increasing. So more and more participants are going into that topic or that subject, and many Bitcoin miners are coming up. So that's why it's a huge laser size. As a result, it becomes slow unless you have some extra technology that is coming up. So as of today, we can say that till now Bitcoins are hot topics and people are working on it. The security is quite good level, but nobody, as I mentioned, nobody can guarantee you. Maybe tomorrow somebody came up with some algorithm which breaks the blockchain and all. So people are also trying to attack blockchains, Bitcoins as well. So it suddenly came, and maybe one day some action may be there and some new technology will suddenly evolve. So nobody knows. So as of now, it's safe.
Okay. Next question. Sometimes when we fill Google form and if it take a little time, then why should we fill a picture captcha?
Uh, I I didn't get your question. Can you please repeat once again?
Okay. Sometimes when we fill Google form and if it take a little time, then why should we fill a picture captcha?
Okay, it's a similar concept like captcha. So machine may think that something illegal is going on. So why you are taking time? Because you are trying to do something else. That means for an attacker is doing something. So a picture comes into picture in means you have to recognize some of the, for example, say sometimes they say that they give you 8 pictures and say that is there any bridge, tick all the images which contains a bus, for example. So you have to find, and sometimes it's very difficult to find all the buses and all. So it's basically to give you a kind of to stop attacks from by AI algorithms. That's why they use this kind of technique. So if some eligible or some feasible time is there, and if it is timeout, then it stops you by providing you this kind of things. But as I mentioned, that AI algorithms are also going on to find the exact solution from an image or from a distorted image. So it's again a parallel games are going on. So that's why to have more security, the captures and this kind of images they usually come into picture.
Okay, sir.
Yeah.
Next question. Is there any extra facility in picture capture?
See, this kind of images are basically there are many images, like 10 different images. Whereas in your, so they are not coming in a single window. So to apply your algorithm, you have to know how many images are there. In every of these small boxes, you have to run your AI algorithm and all. So I think there must be some extra advantages. Otherwise, why they are going to put it? So naively speaking, that could be one of the advantages. Like they are giving different images, but in CAPTCHA you are having in a single block all the pixels you can access at the whole time. But here again you have to do parallelly and all. So AI can do many things. So people are also working on the same thing, attacking the images or captures.
Thank you, sir. Thank you for such an interactive session. Uh, Next, I'm requesting Dr. Bishesh Madam, please take over the session. Please, Madam.
Thank you, Anisha. I think no more questions left. So, and thank you, Professor Kari, for again for your lecture and giving your precious time in this. We are now near the end of our session, and we have been listening to eminent deliberating in the area of relativity and cryptography. All valuable insights gave us a new perspective that we can adopt while discussing. I hope it must have been a beneficial and enriching session for all of our, and hopefully all of you today's platform. Tomorrow we again meet at the same time at 4 p.m. Tomorrow we have three lectures. The details program we will send you in due time. And thanks for your time. We end our session here. Thank you. Good night.
So good night.
We can log off now.